Right now, beneath your feet, buried under miles of rock and sediment, compressed between layers of ancient limestone and sandstone, there might be evidence of a civilization that rose and fell millions of years before the first human ever walked the Earth. Not alien visitors from distant stars who built mysterious monuments and then departed. Not mythical lost continents like Atlantis sinking beneath the waves. But an industrial society that evolved here on this planet, that discovered fire and metallurgy, that learned to harness energy from fossil fuels, that built cities and factories, that altered its climate through carbon emissions, and then vanished so completely, so utterly, that we would have almost no way of knowing it ever existed. This is not science fiction. This is not ancient astronaut speculation or pseudo-archaeological fantasy. This is a serious scientific hypothesis proposed by legitimate researchers at major institutions, published in a peer-reviewed scientific journal, asking one of the most unsettling and profound questions in all of geology. If an advanced industrial civilization existed on Earth tens of millions of years ago, perhaps during the age of dinosaurs or in the mysterious epochs before mammals rose to dominance, would we even be able to detect it? Would there be any trace left for us to find? The question hits you like a geological hammer striking bedrock, shattering comfortable assumptions about our place in planetary history. We think of Earth as our planet, our unique stage, the singular arena where human drama unfolds against a backdrop of natural forces that existed before us and will continue after we're gone. We imagine that the rise of agriculture and cities, the invention of steam engines and computers, the harnessing of fossil fuels and nuclear energy represents something fundamentally new in the 4.5 billion year history of this world. We assume that intelligence leading to technology, that civilization building monuments and machines, that industrial society transforming landscapes and atmospheres is a distinctly human achievement, unprecedented in the annals of terrestrial time. But what if that assumption is wrong? What if it doesn't? What if the Industrial Revolution, this thing we consider so uniquely human, so distinctly modern, so revolutionary, has actually happened before? What if there have been other intelligences, other problem solvers, other tool makers who walked this planet millions of years before our ancestors climbed down from the trees? What if we're not the first? What if Earth has seen this story play out before? The rise of a curious, clever species that discovers how to manipulate its environment, that learns to extract energy from ancient sunlight stored in coal and oil, that builds a technological civilization, and then either evolves beyond it or collapses under the weight of its own success. The implications are staggering. Everything we think we know about our uniqueness, our special place in nature, the unprecedented character of human civilization, all of it might need to be reconsidered. Not because we've found definitive proof of ancient civilizations, we haven't, but because the very possibility forces us to examine what we mean by proof, what counts as evidence, and what the limitations are of our ability to read Earth's ancient past. In 2018, astrophysicist Adam Frank from the University of Rochester and climate scientist Gavin Schmidt, who serves as director of NASA's Goddard Institute for Space Studies, published a paper with a title that sounds like it belongs in a science fiction novel, or perhaps an episode of your favourite space-themed television series, The Silurian Hypothesis. Would it be possible to detect an industrial civilization in the geological record? The paper appeared in the International Journal of Astrobiology, a respected peer-reviewed publication that focuses on the search for life beyond Earth and the conditions that make life possible throughout the universe. The name they chose for their hypothesis comes from Doctor Who, that long-running British television series that has captivated audiences since 1963, where a time-travelling alien known as the Doctor encounters every imaginable cosmic oddity across space and time. In one particularly memorable serial from 1970, titled Doctor Who and the Silurians, the Doctor discovers an ancient race called the Silurians, intelligent reptilian humanoids who built an advanced technological civilization on Earth millions of years before humans evolved, long before mammals even became the dominant form of life. According to the show's mythology, these reptile people developed science and technology, built cities underground, and when their astronomers detected what they mistakenly believed was an apocalyptic threat from space, they retreated into deep hibernation chambers, planning to sleep through the disaster and re-emerge when it was safe. Instead, they slept for millions of years, forgotten by time, buried under layers of geological history, while mammals inherited the surface world and eventually gave rise to humanity. The television series took considerable liberties with science, obviously. Reptilian humanoids with advanced technology stretches credibility on multiple fronts. But the core concept, the idea that an intelligent species could arise, build a civilization, and then disappear so completely that later inhabitants of the planet would have no knowledge of them, that's the kernel Schmidt extracted and subjected to rigorous scientific analysis. Schmidt chose this name with deliberate, knowing irony, making clear from the outset that they were engaging in a thought experiment rather than making an actual claim. They're not suggesting that reptile people ruled prehistoric Earth. They're not arguing that there were cities during the Cretaceous period, or factories in the Triassic. What they're asking is something far more subtle and scientifically rigorous, setting aside the question of what form such a civilization might take or which species might have created it, and focusing purely on the geological record and our ability to read it. Could we actually detect the traces of a long-vanished industrial society? If such a civilization had existed 50 million years ago, or 100 million, or 200 million, and if it had lasted for thousands of years before ending, either through gradual decline or catastrophic collapse, what evidence would remain? What would we look for? And critically, how confident could we be in distinguishing technological signatures from natural phenomena? The answer they arrived at through careful analysis is deeply uncomfortable for anyone who assumes we have a complete, or even mostly complete understanding of Earth's deep past. The answer is, maybe not. Maybe such a civilization could have existed, and we would have almost no way of proving it. The evidence might be too degraded, too ambiguous, too easily mistaken for natural processes. We might be blind to it even if we were looking directly at it. This is not ancient alien nonsense peddled by cable television documentaries asking leading questions while ominous music plays in the background. This is not pyramids attributed to extraterrestrials, or crystal skulls with supposed mystical powers, or lost continents populated by advanced pre-human societies that possessed anti-gravity technology. This is legitimate, credentialed scientists at the top of their respective fields using the rigorous tools of geology, climatology, geochemistry, and astrobiology to explore the outer limits of what we can know about Earth's deep past. They're asking hard questions about epistemology, about the nature of evidence, about how we construct historical narratives when the evidence is fragmentary and ambiguous. And what they discovered through this exercise is that the past is far more opaque than we typically admit in popular science communication, or even in many professional geological contexts. The geological record, that layered chronicle of stone that records Earth's history like a vast library written in rock, is not a complete book with all its pages intact. It's not even a complete chapter or a complete set of paragraphs. It's scattered pages, water-damaged and faded, with enormous sections torn out entirely, others rendered illegible by time and transformation, and still others never written in the first place because the conditions for preservation didn't exist. We're reading fragments, interpolating between massive gaps, making educated guesses and building complex models about what might have been written in the enormous spaces now lost to erosion, to subduction, to metamorphism, and to the relentless grinding of geological time. Think of it this way. If you found a book where 95% of the pages were missing, could you reconstruct the full story with confidence? Could you be certain about events that occurred in chapters you can't read? Could you prove that certain events didn't happen, or would you simply lack evidence that they did? This is the situation geologists face when studying deep time, and the Silurian Hypothesis exposes this limitation in stark terms. The hypothesis also forces us to confront questions about our own legacy, questions that become increasingly urgent as we grapple with climate change, resource depletion, and the long-term sustainability of industrial civilization. If previous civilizations existed and collapsed, leaving only faint traces, what does that tell us about the permanence of our own achievements? What will remain of us in 50 million years? If we fail, if our civilization collapses under the weight of environmental destruction or resource exhaustion, will future intelligent species even know we were here? And if they do detect our traces, what story will those traces tell? If you're ready to question everything you think you know about humanity's place in Earth's story, hit that like button and subscribe. We're about to descend into deep time, to explore the boundaries of what can be known and what must forever remain mystery. The journey begins with understanding just how much of Earth's past is hidden from us. 4.5 billion years. That's how old Earth is, give or take about 50 million years based on radiometric dating of the oldest rocks and meteorites. 4,500 million years, 4,500 million years. However you phrase it, the number is so incomprehensibly large that it becomes essentially meaningless to human cognition. Our brains did not evolve to grasp such timescales. We can write the number, we can perform mathematical operations with it, we can compare it to other numbers, but we cannot truly viscerally comprehend what that duration of time means. Try this exercise. Hold your arms out to either side as wide as they'll go. Imagine that span represents all of Earth history, from the formation of the planet to this present moment. The formation of Earth happens at your left fingertip. The present moment is your right fingertip. Now, where do humans appear on that timeline? How much of that span do we occupy? If you filed down your right fingernail with a single stroke of a nail file, you would remove more time than all of human history. The entire span of genus Homo, including all our ancestral species, all the Australopithecines and early hominins, all of that fits into the tiny bit of keratin you could remove with one swipe of an emery board. Homo sapiens, our specific species, anatomically modern, behaviourally complex, capable of language and symbolic thought and abstract reasoning, we've existed for maybe 300,000 years. That's not even visible on the outstretched arms timeline. That's a thickness far thinner than a single cell. 300,000 years sounds like a long time when you're sitting here experiencing one day at a time. It's roughly 12,000 human generations. It's long enough for our species to spread from Africa to every corner of the globe, to adapt to radically different environments from Arctic tundra to tropical rainforest to high-altitude mountains. It's long enough for us to go through multiple ice ages and warm periods. But place that against Earth's age, 300,000 years into 4.5 billion years, and we've been here for 0.0067% of Earth's existence. Less than 0.007%. Not even 0.1%. A geological eye blink so brief that if you literally blinked, you'd miss it. But even that tiny fraction overstates our significance in geological terms, because for the vast majority of those 300,000 years, we lived in small nomadic bands of hunter-gatherers, leaving barely any permanent trace on the landscape. We made stone tools, yes. We created art, yes. We buried our dead with grave goods, suggesting complex symbolic thought and perhaps religious beliefs. But in terms of geological impact, in terms of altering the fundamental chemistry of the atmosphere, or the composition of sediments or the global climate system, we're essentially invisible for most of our existence. Agriculture, the deliberate cultivation of crops and domestication of animals, emerged independently in several locations around the world starting roughly 10,000 to 12,000 years ago. This was revolutionary. It allowed larger populations, permanent settlements, specialization of labor, the accumulation of surplus food that could support people who didn't directly produce food, priests and craftspeople, and eventually scientists and engineers. But even agriculture didn't massively alter the geological record in ways that would be clearly detectable millions of years hence. A cleared field returns to forest within decades if abandoned. Plough marks in soil get mixed away by bioturbation, the action of burrowing animals and plant roots. Ancient agricultural terraces survive in some landscapes, but they're geologically recent features that would erode away over deep time. Cities arose perhaps 5,000 to 6,000 years ago, first in Mesopotamia, then independently in Egypt, the Indus Valley, China, Mesoamerica, and elsewhere. The first true cities with dense populations, monumental architecture, complex social hierarchies, writing systems, legal codes. This was another revolution. But cities before the Industrial Age were built primarily from mud brick, fired brick, stone and wood. These materials don't survive well over geological time. Mud brick dissolves in rain, wood rots, even stone structures crumble and erode. The ruins we can still visit today, Egyptian pyramids and Greek temples and Roman aqueducts and Mayan pyramids, these are all geologically young, dating from within the last few thousand years. Give them 10 million years of erosion, weathering and tectonic activity, and there would be nothing recognizable left. Perhaps some stone blocks scattered and incorporated into sediments, indistinguishable from natural rock fragments, that's all. and the industrial civilization that we now consider the defining feature of modern human society, the thing that makes us qualitatively different from all previous eras of human history, that's existed for roughly 300 years in its recognizable form, since the development of mass production methods, steam engines, widespread coal mining, and the systematic exploitation of fossil fuels for energy. 300 years out of 4.5 billion, out of 300,000 years of Homo sapiens, out of 10,000 years of agriculture, out of 5,000 years of urban civilization. 300 years is nothing. It's 12 human generations. It's the span from your great-great-great-great-great-great-great-great-great-grandparents to you. It's less time than separates us from the height of the Renaissance. It's less than the age of some individual trees still living on this planet. And yet this brief pulse of industry, this blink and you miss it moment of coal burning and oil extracting and machine building, this is what we consider revolutionary, unprecedented, permanent. Put another way, if Earth's entire 4.5 billion year history were compressed into a single 24-hour day, with the planet forming at midnight, humans would appear at 4 seconds before the next midnight. Not 4 minutes, not 4 hours, 4 seconds. Industrial civilization would occupy the last 100th of a second, a duration shorter than the time it takes a camera shutter to click. We are unimaginably, incomprehensibly recent arrivals, showing up at the very, very end of a very, very, very long story that's been unfolding for eons before we existed. Now, imagine trying to detect evidence of something that lasted only 300 years, an eye blink, a camera shutter click, but happened not at the end of the story where we could examine it easily, but somewhere in the middle, buried under billions of years of subsequent geological history. Say, 100 million years ago, during the Cretaceous period when dinosaurs roamed and flowering plants were just beginning to diversify, or 200 million years ago in the early Jurassic, when the supercontinent Pangaea was beginning to break apart, or 400 million years ago in the Devonian period, when the first forests were spreading across the continents and fish were beginning to venture onto land. How would you do it? What would you look for? What traces could possibly survive that span of time, especially when the thing you're looking for was so brief? This is the central challenge of the Silurian Hypothesis, and to understand why it's so monumentally difficult, you need to grasp just how incomplete, how fragmentary, how full of gaps our knowledge of deep time really is. The geological record is Earth's autobiography, written in layers of sedimentary rock stacked like pages in a monumental book. Each stratum, each layer, represents a snapshot of ancient environments preserved through the patient processes of deposition and lithification. Sand settles in ancient rivers and becomes sandstone. Mud accumulates on seafloors and becomes shale. Tiny shells of marine organisms rain down in uncountable trillions and become limestone. Volcanic ash falls and compacts into distinctive layers that can be correlated across continents. Geologists read these layers like pages in a chronicle, identifying fossils embedded within them, analysing chemical compositions, measuring grain sizes and sorting, reconstructing vanished ecosystems from the clues preserved in stone. It's an astonishing achievement of human ingenuity and persistence, this reading of the rocks. From scattered fragments, from outcrops and road cuts and quarries and drill cores, geologists have assembled a remarkably detailed picture of Earth's history. We know about the first single-celled organisms that appeared at least 3.5 billion years ago, preserved as microscopic fossils and chemical signatures in some of Earth's oldest rocks. We know about the Great Oxidation Event around 2.4 billion years ago, when photosynthetic bacteria began producing oxygen, fundamentally transforming the atmosphere and enabling new forms of life. We know about snowball Earth events when the entire planet apparently froze over. We know about the Cambrian explosion 540 million years ago when complex animals suddenly appeared in the fossil record with hard shells and diverse body plans. We know about the rise and fall of dinosaurs, from ancient sea reptiles to flying pterosaurs to the terrestrial giants that dominated ecosystems for 165 million years. We know about ice ages and tropical epochs, about times when palm trees grew in the Arctic and crocodiles swam in Greenland, and other times when ice sheets a mile thick covered Chicago and New York. This reconstruction is one of humanity's great intellectual achievements, comparable to decoding the structure of DNA or mapping the human genome or discovering the laws of physics. The level of detail we've achieved is remarkable. We can track changes in atmospheric carbon dioxide over hundreds of millions of years. We can reconstruct ancient ocean temperatures from oxygen isotopes in fossilized shells. We can date rocks to within a few million years or better using radiometric techniques. We can trace the movement of continents through time, watching as Pangaea assembled and then broke apart as the Atlantic Ocean opened, as India crashed into Asia and raised the Himalayas. We can identify mass extinction events and track the recovery of ecosystems afterward. But, and this is crucial, all of this remarkable knowledge comes with an enormous caveat. The geological record is not a continuous, unbroken chronicle. It's riddled with gaps, with enormous spans of missing time where we have almost no information at all, or where our information is so fragmentary and ambiguous that we can barely make sense of it. Erosion destroys rock layers, grinding mountains down to plains, carving canyons through sediments, washing material away to be deposited elsewhere or lost to the oceans. Tectonic forces crumple strata, fold them, fault them, push them deep underground where heat and pressure transform them beyond recognition through metamorphism. Subduction zones drag ocean floor back into Earth's mantle at tectonic plate boundaries, completely erasing whatever history those rocks contained, recycling the material back into magma to eventually erupt from volcanoes and begin the cycle again. And the older the period you're examining, the less rock remains and the more fragmentary the record becomes. This is simply a matter of time's destructive power. A rock layer deposited 10 million years ago has had 10 million years to be eroded, buried, deformed, or subducted. A rock layer deposited 100 million years ago has had 100 million years of such processes working on it. A layer from 500 million years ago has endured 500 million years of geological violence. The odds that it survives intact in a form we can access and study decrease exponentially with age. Charles Darwin understood this problem intimately, and it troubled him. In On the Origin of Species, published in 1859, he devoted considerable space to what he called the imperfection of the geological record. His theory of evolution by natural selection predicted that species should transform gradually over time through the accumulation of small beneficial variations. If that were true, there should be countless intermediate forms preserved in the fossil record, smoothly transitioning from one species to another. But the fossil record didn't show that. It showed sudden appearances of new species, long periods of apparent stasis where species didn't change much, and then sudden disappearances. Where were all the transitional forms? Where were the intermediates? Critics of evolution seized on this apparent problem, arguing that the absence of transitional fossils disproved Darwin's theory. Darwin's response was to point to the geological record's incompleteness. He wrote one of the most eloquent passages in all of scientific literature describing this limitation. For my part, following out Lyell's metaphor, I look at the natural geological record as a history of the world imperfectly kept and written in a changing dialect. Of this history we possess the last volume alone, relating only to 2 or 3 countries. Of this volume, only here and there a short chapter has been preserved, and of each page only here and there a few lines. Think about what Darwin is saying. Imagine you're trying to understand the history of human civilization. But the only documents you have access to are a few random pages from books written in the last 1,000 years, and those pages come only from Britain and France. You have page 47 from one book, page 203 from another, page 89 from a third. You don't have the covers, so you don't know the titles. You don't have the context. The pages themselves are damaged, with whole sections illegible, and this fragmentary material is all you have to reconstruct thousands of years of human history across the entire globe. That's what geologists face when studying deep time. Darwin attributed the absence of transitional fossils to this imperfection of preservation, and he was largely correct. We now know that fossilization is extraordinarily rare, that most organisms that ever lived left no fossils at all, and that the apparent jumps in the fossil record often result from the incompleteness of preservation, rather than from actual jumps in evolution. We've since found many transitional forms that Darwin could only predict must exist. Fish with proto-limbs transitioning to tetrapods, reptiles with features transitional to mammals, dinosaurs with feathers transitioning to birds. The fossil record has improved enormously since Darwin's time, but it remains fundamentally incomplete. Consider a simple, concrete example that illustrates just how sparse the record can be. Less than 3% of Earth's current land surface is urbanized by human activity. All of our cities, all of our roads, all of our airports and factories and shopping centres, all of our concrete and steel and glass infrastructure covers less than 3% of the continents. The remaining 97% is forest, grassland, desert, tundra, farmland, wilderness, mountains, rivers, lakes, ice sheets, areas where humans have impact but haven't fundamentally paved over or built on top of the surface. Now imagine what happens to those cities over geological time, over millions of years. Buildings crumble, steel oxidizes and flakes away, concrete fractures as water seeps into tiny cracks, freezes and expands. Foundations undermine as rivers change course, as coastlines shift with sea level changes, as hillsides slump and valleys fill. Vegetation reclaims cleared areas within decades if they're abandoned. Trees grow through pavement, roots penetrate foundations. Within a few thousand years, visible surface structures would be gone or unrecognizable. Within tens of thousands of years, almost nothing would remain at the surface. And then geological processes would continue working on whatever ruins remained. Tectonic plates are constantly in motion, grinding slowly but inexorably. Some regions get lifted into mountains, others get pushed down and buried under new sediments. Coastlines migrate as ice caps wax and wane, locking up water or releasing it, causing sea levels to fall by hundreds of feet during ice ages and rise by similar amounts during warm periods. Rivers carve new channels, wind erodes exposed rock, rain dissolves limestone, heat and pressure transform sediments into metamorphic rocks, erasing original features. There's a particularly striking example of missing time in the rock record at the Black Canyon of the Gunnison in Colorado, where the Gunnison River has carved a spectacularly deep canyon through layered rock. At the bottom of the canyon, you find dark, ancient metamorphic rock called the Black Canyon gneiss, contorted and crystalline, formed from even older sediments that were buried deep, heated, and compressed about 1.7 billion years ago. These are among the oldest rocks exposed anywhere in North America, a window into deep Proterozoic time. Directly on top of the gneiss, separated by a razor-sharp boundary called an unconformity, you find bright yellow Entrada sandstone from the Jurassic period, deposited in ancient sand dunes a mere 180 million years ago. That boundary, that unconformity, represents a missing interval of 1.5 billion years. 1.5 billion years. More than 1 billion years of Earth history simply gone, erased, unrecorded. During that vast span of time, continents assembled and broke apart, oceans opened and closed, life evolved from single cells to complex multicellular organisms, ice ages came and went, volcanoes erupted, mountains rose and eroded away. All of that happened, but at this location no record of it exists. Either sediments were never deposited here, or they were deposited and then completely eroded away before the Jurassic sand began to accumulate. 1,500 million years, and we have no idea what happened during that vast expanse of time in this location because the rock that would tell us simply no longer exists. This is not unusual. This is not some weird anomaly specific to the Black Canyon. The geological record everywhere is full of such unconformities, gaps representing more time missing than preserved, and crucially, the further back in time you go, the worse the problem becomes, because older rocks have had more time to be destroyed or transformed. Very little of Earth's exposed surface consists of rock older than the Quaternary period, which began only 2.6 million years ago. Rocks from truly ancient times, from hundreds of millions of years ago, are rare and often buried deep beneath younger deposits. This means that if you want to find evidence of something from, say, the Carboniferous period, 350 million years ago, you're dealing with a rock record that's fragmentary at best and often completely absent. Now, add another complication. Even when ancient rocks do survive, they've often been transformed by heat and pressure. Metamorphism can erase or alter original features. Fossils can be destroyed. Chemical signatures can be reset. The tools geologists use to read Earth's history become less and less effective the older the rocks they're examining. Dating techniques that work wonderfully for recent history become uncertain or impossible for deep time. You're left making inferences, constructing models, arguing about interpretations. This is the context in which Frank and Schmidt posed their question. If an industrial civilization arose on Earth not thousands of years ago but millions, operating during a time when the geological record is already fragmentary and incomplete, What chance would we have of detecting it? What traces would such a civilization leave? And more importantly, what traces would survive long enough for us to find them? The answer depends critically on understanding what actually gets preserved over millions of years. And to understand that, we need to explore how fossilization works and why it's so rare. When you visit a natural history museum and stand before a complete articulated skeleton of a Tyrannosaurus rex or a Triceratops, mounted on steel supports with its bones assembled into a lifelike pose, you're looking at something profoundly, almost impossibly unlikely. That animal, let's say it was a T-Rex, died roughly 66 to 68 million years ago, give or take a few 100,000 years based on radiometric dating of the volcanic ash layers above and below the fossil bed. At the moment of death, perhaps it was killed by disease or starvation, or injury or old age. Maybe it drowned in a flood, or died of infection from a wound sustained in combat with a rival. We usually don't know the specific cause of death, though sometimes we can infer it from damage to bones or the circumstances of preservation. What happened next was critical and highly improbable. The carcass needed to avoid being completely scattered and consumed by scavengers. Tyrannosaurus rex was the apex predator of its ecosystem, so it wouldn't have been eaten by larger animals, but smaller scavengers and carrion feeders would have descended on the body. Crocodilians would have torn at flesh. Smaller dinosaurs and pterosaurs would have picked at remains. Insects would have laid eggs in decaying tissue. Bacteria would have begun decomposing soft parts. In most cases, this process results in the complete disintegration of the body. Bones get scattered across a wide area, broken and gnawed, left exposed on the surface where sun and rain and freezing and thawing cause them to crack and crumble. Within a few years or decades, nothing recognizable remains, but occasionally, rarely, the body gets rapidly buried. A flood might dump sand and mud over the carcass. A landslide might cover it. In ancient wetlands, the animal might die and sink into soft sediment that engulfs it before scavengers can fully disarticulate the skeleton. This rapid burial is the first critical step in fossilization. The sediment protects the bones from scavengers, from weathering, from the destructive forces that normally erase all trace of the dead. But burial alone isn't enough. The bones need to be in an environment where preservation can occur rather than dissolution. Oxygen is the enemy of preservation because it enables aerobic bacteria to rapidly break down organic material. The ideal environment for fossilization is anoxic, meaning oxygen depleted and often underwater. Ancient lake beds, river channels, marine environments, these are the settings where fossils form most readily. The bones also need to be in sediment with the right chemical properties. If the groundwater is too acidic, it will dissolve bone. If it's too alkaline, different problems arise. The chemistry needs to be in a Goldilocks zone that allows mineralization to occur. What happens during mineralization is remarkable. Bone, despite seeming solid, is actually porous at a microscopic level. It has tiny spaces, channels that in living bone carry blood vessels and contain bone marrow. After burial, over hundreds or thousands of years, groundwater percolates through the sediment and through the bone. This groundwater carries dissolved minerals, typically silica or calcium carbonate, sometimes iron compounds. As the water flows through the bone's porous structure, these minerals gradually precipitate out, filling the tiny spaces, reinforcing the bone's structure. Eventually, the original organic material, the collagen and proteins that made up the bone matrix, decays and is replaced molecule by molecule with minerals. What you end up with is a stone replica of the original bone, a fossil that retains the shape and even microscopic details of the original structure, but is made of entirely different material. This process, called permineralization, can take anywhere from a few thousand years to a few million years depending on conditions. It's the most common form of fossilization for bones and teeth. But even after a bone is permineralized and turned into stone, the fossil is not safe. The rock layer containing it must survive over geological time. It must avoid being eroded away completely. It must avoid being metamorphosed by heat and pressure to the point where original structures are destroyed. It must avoid being subducted into Earth's mantle. It must eventually be re-exposed at the surface through erosion or tectonic uplift so that someone can find it. And crucially, someone has to actually find it, has to recognize it as a fossil, has to recover it carefully without destroying it during excavation. Every step in this chain has a low probability. The combination of all those low probabilities makes fossilization extraordinarily, vanishingly rare. Paleontologists have done the math on this. They estimate that far less than 1% of all organisms that ever lived became fossils. Some estimates for vertebrates go as low as one individual in a million becoming fossilized. For some groups, the odds are even worse. Soft-bodied organisms that lacked hard parts have fossilization rates that might be 1 in a billion or worse. Think about that. For every fossil we find, there were millions or billions of individuals who lived and died and left absolutely no trace whatsoever, as if they had never existed. Fossilization requires very specific environmental conditions that are by no means universal across the planet. Marine environments, particularly shallow seas and river deltas where sediment accumulates quickly, these are the settings most conducive to preservation. Dead organisms settle to the seafloor or lake bottom, get covered rapidly by mud or sand carried by currents, and begin the slow transformation into stone. This is why marine invertebrates with hard shells are disproportionately common in the fossil record. Clams, snails, brachiopods, trilobites, ammonites. These animals lived in environments ideal for fossilization, and they had hard parts that could be mineralized. Their fossil record is actually fairly good, relatively speaking. Terrestrial organisms, animals and plants that lived on land have much lower fossilization rates because terrestrial environments are generally less conducive to preservation. Bodies left on land surface are exposed to scavengers, weathering, decomposition in oxygen-rich air. They might lie there for months or years before being buried, during which time they disintegrate. Even if burial eventually occurs, perhaps by windblown dust or sediment from a seasonal flood, it's often too late. The bones have already scattered, dried out, cracked apart. Fossilization of terrestrial organisms requires special circumstances. An animal dying in or near a body of water that can rapidly bury it, or dying in a cave where conditions are stable, or being buried by volcanic ash or a mudslide. But even in ideal conditions, most organic material decays long before mineralization can occur. Soft tissues, the skin and muscle and organs and connective tissues that make up most of an animal's body. They rot away in days or weeks under most circumstances. What can be preserved are the hard parts: bones, teeth, shells, wood, anything made of durable mineral that resists decay. This is why we know so much about the skeletons of extinct animals, but so little about their soft anatomy. We can reconstruct how a stegosaurus's bones fit together, but we're largely guessing about the appearance of its skin, the structure of its muscles, its internal organs. We have some skin impressions, some fossilized soft tissue from exceptional preservation, but it's rare. There are locations, rare and precious, where soft tissue preservation does occur. The Burgess Shale in British Columbia contains fossils from about 508 million years ago from the Middle Cambrian period, and it preserves an extraordinary array of soft-bodied organisms that normally leave no trace. We can see impressions of guts, gills, antennae, fine details of organisms that would otherwise be completely unknown. The Solnhofen limestone in Bavaria preserves exquisite fossils including Archaeopteryx, the famous transitional fossil between dinosaurs and birds, with feather impressions so detailed you can see individual barbs and barbules. These exceptional preservation sites, called Lagerstätten, are invaluable precisely because they're so rare. They give us windows into ancient ecosystems that would otherwise be invisible. Now consider what all of this means for detecting evidence of technology rather than biological organisms. Tools, buildings, machines, infrastructure, all the artifacts of industrial civilization. These are not biological structures with cells and organic material that can undergo permineralization. They don't have hard parts in the paleontological sense. They're made of materials that respond very differently to geological processes. Metal corrodes through oxidation, forming rust or other oxide compounds that flake away and become indistinguishable from natural iron-rich sediments. A steel beam from a skyscraper, buried and subjected to groundwater flow for 1 million years, would rust completely, leaving only a layer of iron oxide that looks like any other iron deposit. You couldn't identify it as artificial metal versus natural iron ore without sophisticated geochemical analysis, and even then you might not be certain. Glass, which seems permanent and inert, is actually thermodynamically unstable over long timescales. It slowly devitrifies, crystallizes, and eventually dissolves in groundwater, or transforms into other silica minerals that are indistinguishable from natural quartz or chert. Ancient glass beads from a few thousand years ago sometimes survive, showing us that glass can persist for short periods in geological terms, but over millions of years glass artifacts would vanish or become unrecognizable. Concrete, that fundamental material of modern civilization, is essentially artificial sedimentary rock. It's made from limestone derivatives mixed with sand and gravel, not fundamentally different from natural limestone conglomerate. After millions of years of burial, weathering and diagenesis, the chemical transformation that occurs as sediment becomes rock, concrete structures would fracture and crumble, the components would separate, looking like natural limestone clasts in a sedimentary matrix. You'd need very specific analysis to identify it as artificial cement versus natural rock, and that analysis would require you to already suspect you were looking at something artificial. If you weren't looking for it, you'd probably never notice. Plastic, that seemingly indestructible material that's choking our modern oceans, is chemically unstable over deep time. Yes, plastic persists for decades or centuries in the modern environment, which is precisely why it's such an environmental problem. A plastic bottle tossed in the ocean doesn't biodegrade in any reasonable human timescale, but doesn't biodegrade quickly is very different from survives geological time. Synthetic polymers, the long molecular chains that make up plastics, break down when exposed to ultraviolet light from the sun, to heat, to certain bacteria that have evolved to consume them. The polymer chains break into shorter and shorter fragments, eventually becoming microplastics, then nanoplastics, then individual monomers that can be metabolized by microorganisms or incorporated into natural carbon cycles. Scientists studying this question have found that plastic does leave traces in sediment cores. You can detect microplastic particles in marine sediments going back to the 1950s when mass production of plastics began, and the abundance increases exponentially to the present, tracking the growth of global plastic production. This creates a marker layer, a distinctive signature that future geologists could theoretically use to identify the Anthropocene, the proposed geological epoch defined by human impact. But the key word is theoretically. These studies are looking at sediments only decades to maybe a century old. The plastics are still relatively fresh, chemically speaking. What happens over 1 million years? Over 10 million? Over 50 million? The deeper you go in the sedimentary record, the more time the plastic has had to degrade. UV light might be absent in buried sediment, but heat from burial isn't. Chemical reactions still occur, just more slowly. Bacteria continue evolving, and some lineages are already developing plastic digesting capabilities. Given millions of years, the distinctive molecular structure of synthetic polymers would degrade to the point where distinguishing them from natural organic compounds becomes extraordinarily difficult, if not impossible. One study of Mediterranean sediments looked at the preservation of microplastics in undisturbed deep ocean environments, and found that while plastics are well preserved in the absence of UV light and mechanical disruption, they still show signs of oxidation and chemical breakdown even in these ideal conditions. The researchers noted that the long-term fate of plastics in the geological record remains uncertain, but preliminary evidence suggests significant degradation over timescales of tens of thousands of years, let alone millions. And that's plastic, a material we specifically engineered to resist degradation. Imagine what happens to other technological materials over deep time. Aluminum, which doesn't rust like iron but does form a thin oxide layer, would gradually oxidize completely given sufficient time and exposure to oxygen or water. Copper corrodes into green copper carbonate, which eventually dissolves or gets incorporated into sediments as copper-bearing minerals indistinguishable from natural copper deposits. Rubber decomposes. Textiles rot or burn or get chemically broken down by bacteria. Paper, made from plant fibers, biodegrades relatively quickly, lasting at most a few centuries in most environments before crumbling to dust. What about things that are truly permanent? Materials that don't break down chemically? Nuclear waste comes to mind. Plutonium-244, a transuranic element that does not occur naturally anywhere on Earth outside of supernova remnants, would be definitive proof of artificial nuclear reactions if you found it in sediment. It couldn't have gotten there naturally, but plutonium-244 has a half-life of 80 million years, which sounds long, and it is by human standards, but it's not infinite. After 80 million years, half of the plutonium, 244 atoms have decayed into other elements. After 160 million years, only a quarter remains. After 320 million years, you're down to 1/16 of the original amount. After a billion years, the plutonium-244 is effectively gone, decayed through multiple generations of daughter isotopes until you're left with stable elements that tell you nothing about their nuclear origin. Other artificial isotopes have much shorter half-lives and thus vanish much faster. Plutonium-239, the isotope used in nuclear weapons and reactors, has a half-life of only 24,100 years. That's long enough to be a serious waste disposal problem for human civilization. Long enough that we need to think carefully about where we store it and how we warn people 10,000 years hence not to dig it up. But after a million years, it's gone, decayed into uranium and then into various other elements, undetectable except by the most sensitive isotopic analysis, and even then only if you knew exactly what you were looking for and where. Cesium-137, produced by nuclear fission and used as a marker for dating recent sediments because it spikes in the 1960s during atmospheric nuclear testing, has a half-life of about 30 years. It's useful for dating sediments from the last century, but Cesium-137 from 10,000 years ago would be literally undetectable, decayed away completely. Tritium, carbon-14, strontium-90. All the various radioactive isotopes we produce and worry about, they all have half-lives measured in years, decades, or at most thousands of years. Over geological time, they vanish, becoming part of the natural background of stable isotopes, so direct physical artifacts don't survive deep time, or if they do survive, they're transformed beyond recognition. If previous industrial civilizations existed millions of years ago, we wouldn't find their buildings or their machines or their power plants or their waste dumps. All of that would be gone, ground down by erosion, corroded by chemistry, metamorphosed by heat and pressure, subducted into the mantle, scattered and diluted until undetectable. Does this mean there's no possible way to detect such a civilization? Not necessarily. The key is to look not for direct artifacts, but for indirect evidence, chemical and isotopic signatures that indicate industrial activity, even when the artifacts themselves have vanished. This shifts the question from, can we find their stuff, to, can we find the traces their stuff left in the environment? And that's a very different, much more subtle question. For instance, consider fertilizers. Modern agriculture depends on synthetic nitrogen compounds, produced industrially through the Haber-Bosch process. These fertilizers run off fields into rivers and oceans, where they alter the chemistry of sediments. A dramatic spike in nitrogen levels in sediment cores could indicate intensive agriculture. But nitrogen is a common element, and there are natural processes that can concentrate it. Distinguishing an artificial spike from a natural one requires careful analysis and context. After millions of years, with the original sediments altered by diagenesis, the chemical changes that occur as sediment turns to rock, such distinctions become very difficult. Or think about carbon isotopes. Carbon has two stable forms, carbon-12 and carbon-13. Plants preferentially take up the lighter carbon-12 during photosynthesis, so organic carbon, the carbon from living things, has a slightly different isotopic ratio than inorganic carbon from rocks. Burning fossil fuels releases carbon with a specific isotopic signature that's detectably different from carbon released by volcanic activity or forest fires. This is one way climate scientists know that the current rise in atmospheric carbon dioxide is from human fossil fuel use rather than natural causes. The isotope ratios prove it, but here's the catch. After that, carbon gets incorporated into sediments, and those sediments get buried and heated and transformed over millions of years. The isotopic ratios can shift. Diagenetic processes can alter the signature, and even if the signature survives, interpreting it becomes ambiguous. A negative excursion in carbon-13 could indicate massive burning of organic carbon, but it could also be caused by natural events like volcanic eruptions releasing carbon from limestone, or massive die-offs of organisms altering the ocean chemistry, or changes in ocean circulation patterns. Without additional context, without other confirming evidence, you can't definitively say this was an industrial civilization burning coal. This is the fundamental problem. Individual pieces of evidence are ambiguous. Natural processes can mimic technological signatures, and the longer the time since the event, the more degraded and uncertain the evidence becomes. You need multiple independent lines of evidence all pointing in the same direction, You need chemical anomalies, isotopic shifts, sedimentary changes, all occurring at the same time, all consistent with industrial activity. And even then, you'd be making an argument from circumstantial evidence, not direct proof. The geological record is not designed to preserve evidence of brief technological episodes. It's designed, if we can use that word for an unguided natural process, to record long-term changes in climate, sea level, biosphere. Things that persist for hundreds of thousands or millions of years leave clear traces. Things that happen quickly and then stop, they're much harder to detect. And industrial civilizations by definition are brief. Even if a society lasted for thousands of years, that's a geological instant. The entire span of human civilization, from the first cities to the present, would be represented by a sedimentary layer a few millimeters thick. In most places, that layer would not exist at all because sediment wasn't being deposited there, or it was deposited and then eroded away, or it got ground up and recycled. The chance that such a thin layer would survive would be in a location where we could find it and would contain unambiguous evidence of technology. Those odds are not good, but they're not zero. Which brings us to one of the most intriguing aspects of the Silurian Hypothesis, the question of when. When could such a civilization have existed? And the answer Frank and Schmidt propose is surprisingly specific. There is a period in Earth's history that seems almost tailor-made for industrial civilization. A time when vast reserves of chemical energy lay ready to be tapped, when the raw materials for industry were abundant, when the conditions existed for a technological society to arise and flourish. That period is the Carboniferous, roughly 350 million years ago. The name itself is a clue. Carboniferous means coal-bearing, and the period was named by British geologists in the early 1800s for the thick coal seams they found in rocks of that age. These coal deposits, and others like them around the world, are the foundation of the Industrial Revolution. They are the concentrated carbon that powered steam engines, blast furnaces, electrical generators. Without coal, human technological civilization would have developed very differently, if it developed at all. And virtually all of that coal was laid down during a relatively brief window in Earth's history, primarily in the Carboniferous and into the early Permian periods. This wasn't a coincidence. The Carboniferous was a time of incredible biological productivity, specifically in terms of plant life. This was the era of vast swamp forests, where trees grew to enormous heights in tropical wetlands that covered much of the planet. But these weren't trees as we know them today. The dominant plants were giant lycopods, club mosses that grew 30 meters tall with trunks a meter across. Horsetails reached heights of 20 meters. Tree ferns spread their fronds in dense canopies. These forests were alien landscapes, more bizarre than anything in a science fiction film. And when these plants died, they didn't fully decompose. This is one of the key peculiarities of the Carboniferous. For most of Earth's history, when a tree falls, fungi and bacteria break it down, recycling the carbon back into the ecosystem. But during the Carboniferous, the fungi that could decompose lignin, the tough polymer that makes wood rigid, had not yet fully evolved. The bacteria that could process cellulose were rare or ineffective. So when trees fell, they just piled up, layer upon layer, compressed under their own weight into thick mats of plant material. As sea levels fluctuated, these swamp forests would be flooded, buried under marine sediments. Then sea levels would drop, the swamps would re-establish, and the cycle would repeat. Each cycle left a layer of compressed plant matter, peat, which over millions of years of burial, heat and pressure transformed into coal. The result was seam after seam of high-quality black coal, sometimes meters thick, stacked like pages in a book. Geologists can count these cycles by counting the coal layers. Some regions have dozens of seams, each representing a distinct swamp forest that flourished but was buried and gave rise to another. By the end of the Carboniferous, Earth had accumulated vast deposits of fossil carbon. Frank and Schmidt's key insight is that from this point onward, the raw material existed for industrial civilization. Any species that evolved intelligence, that discovered fire and developed metallurgy, would eventually find coal, and coal is a remarkably useful substance. It's energy-dense, easily extracted from near-surface deposits, straightforward to burn. It enabled the steam engine because steam engines need concentrated heat, and coal provides that in a portable, storable form. Oil and natural gas are wonderful energy sources, but they're harder to find and harder to exploit without already having industrial infrastructure. Coal is the gateway fuel, the one that lets you bootstrap your way to higher technology. So the question becomes, could an intelligent species have arisen during or after the Carboniferous and developed an industrial civilization based on burning these coal deposits? Biologically, it's not impossible. The Carboniferous saw the evolution of the first reptiles, early amniotes that no longer needed to return to water to breed. These were small lizard-like creatures, but they represented a significant evolutionary innovation. Over the following periods, reptiles diversified into all sorts of forms, eventually giving rise to dinosaurs, pterosaurs, marine reptiles. Intelligence, in the sense of problem-solving ability and social complexity, evolved multiple times in different lineages. Birds, mammals, even some dinosaurs show signs of sophisticated cognition. But would intelligence lead to technology? That's less clear. Humans are the only species we know of that developed industrial civilization, and we did it for specific reasons related to our biology and ecology. We have hands capable of fine manipulation. We're social primates with complex communication. We can cooperate in large groups. We have a strange obsession with tools and modification of our environment. And critically, we evolved in Africa during climate fluctuations that may have favoured flexible, innovative behaviour. An entirely different evolutionary path might not lead to technology, even with intelligence. Dolphins are smart but have no hands. Octopuses are remarkably clever but are solitary and short-lived. Crows use tools but lack the social structure and lifespan to accumulate knowledge across generations. Intelligence alone is not enough. You need the right combination of traits, and that combination may be rare. Still, over the vast span of time from the Carboniferous to the present, 350 million years, is it absolutely impossible that some lineage could have hit upon the right combination? Frank and Schmidt weren't arguing that it happened, only that we couldn't rule it out with certainty. If it did happen, say 100 million years ago during the age of dinosaurs, or 250 million years ago in the early Triassic, those civilizations would have had access to coal. They could have burned it, industrialized, altered their climate, and then gone extinct, leaving only the faintest chemical whispers in the sedimentary record. And there's something else to consider. The coal that was laid down in the Carboniferous, that's mostly still there, we've been burning it for only 200 years. In geological terms, we've barely scratched the surface of the world's coal reserves. If a previous industrial civilization had existed and burned coal, they would have depleted some of those deposits. But how would we know? We'd have to find evidence of ancient mining, and after millions of years, mine shafts would have collapsed, filled in, been deformed by tectonic forces until they're unrecognizable. A coal seam that was completely mined out would appear as a gap in the rock record, but such gaps are common for all sorts of geological reasons. You couldn't point to a missing coal layer and confidently say ancient aliens mined this. So the Carboniferous presents both an opportunity and a challenge for the Silurian Hypothesis. It's an opportunity because it marks the point after which industrial civilization becomes theoretically possible. It's a challenge because even if such a civilization existed and exploited coal, proving it from the fragmentary geological record we have is extraordinarily difficult. But there's another angle to consider. What if we stop looking for evidence of what an ancient civilization did to the planet, and instead look at what the planet did to itself? What if there are natural events in Earth's history that might be mistaken for industrial climate change? This brings us to one of the most fascinating and relevant examples, the Paleocene-Eocene thermal maximum. 55 million years ago, something dramatic happened to Earth's climate. Over a period of just a few thousand years, global temperatures spiked by 5 to 8 degrees Celsius. The Arctic Ocean, normally frigid, warmed to subtropical temperatures approaching 23 degrees Celsius. Tropical seas became bathtub hot, reaching 36 degrees Celsius off the coast of West Africa, temperatures that are barely survivable for most marine life. This warming persisted for about 100,000 to 200,000 years before temperatures gradually returned to normal. This event is called the Paleocene-Eocene thermal maximum, or PETM, and it's one of the best-studied rapid climate changes in the geological record. Scientists are fascinated by it because it represents the closest ancient analogue we have to modern anthropogenic climate change. The rate of carbon injection into the atmosphere, the magnitude of the warming, the effects on ecosystems, all bear striking similarities to what we're seeing today and what we project for the future. Understanding the PTM might help us understand where we're headed. But here's what makes it relevant to the Silurian hypothesis. The PETM was caused by a massive release of carbon into the atmosphere. Somewhere between 2,000 and 10,000 gigatons of carbon were added to Earth's carbon cycle over a few thousand years. That carbon had to come from somewhere. The leading theory is that it came from volcanic activity, specifically from massive eruptions associated with the North Atlantic Igneous Province, a huge volcanic field that was active at the time. The volcanoes released carbon dioxide directly, and they also heated up ocean sediments, causing methane hydrates, frozen methane trapped in seafloor sediments, to destabilize and bubble up into the atmosphere, adding even more greenhouse gas. This is a perfectly reasonable natural explanation, and most scientists accept it as the likely cause. But notice the signature of the event: rapid carbon injection, global warming, ocean acidification, mass extinctions in some ecosystems, and rapid evolution in others. If you didn't know about the volcanic activity, if you just looked at the carbon isotope excursion and the climate effects, you could mistake this for industrial civilization burning fossil fuels at a massive scale. In fact, that's one of the points Frank and Schmidt make. The PETM demonstrates that natural events can produce chemical and climate signatures similar to industrial activity. The carbon isotope ratios show a pronounced negative excursion, meaning the carbon that was added was isotopically light, depleted in carbon-13. Fossil fuels are isotopically light because they come from ancient photosynthetic organisms, but so is methane from hydrates, and so is carbon from some types of volcanic emissions. Just looking at the isotope ratios doesn't tell you the source. The PETM lasted for thousands of years in its onset phase and persisted for 100,000 to 200,000 years overall. That's much longer than a human industrial civilization has existed, but it's still geologically brief. In sediment cores, the PETM is often compressed into a layer just a few centimeters thick. If you were looking at that layer millions of years from now, with no context, with no knowledge of Paleocene life or Eocene geology, could you definitively say whether it was caused by volcanism or by civilization? The honest answer is probably yes, with enough analysis. The PETM has been studied extensively, and the evidence points clearly to natural causes. There are volcanic ash layers associated with the carbon excursion. There are geochemical markers of seafloor methane release. There's evidence of increased weathering rates, consistent with more rainfall in a hotter climate. The ecological changes make sense in the context of natural climate shift. Nothing about the PETM requires invoking technology. But imagine a less well-preserved event. Imagine something that happened 200 million years ago, during the Jurassic, where the sedimentary record is fragmentary and ambiguous. You find a layer with elevated carbon content and a negative isotope excursion. How do you know what caused it? You look for context, for associated evidence. But if that evidence is missing or degraded, you're left with uncertainty, and that uncertainty is the space where the Silurian hypothesis lives. Frank and Schmidt aren't claiming the PETM was caused by ancient lizard people burning coal. They're using the PETM to illustrate how difficult it would be to distinguish industrial signals from natural ones, especially with incomplete data. The PETM is a gift to science because it's young enough and well-preserved enough that we can study it in detail. But events from deeper time, from periods where we have far less data, those events might be genuinely ambiguous. There's another aspect of the PETM worth considering. The climate change during the PETM had profound effects on life. Deep-sea organisms suffered mass extinction, with up to 50% of some groups dying out. But life adapted. New species evolved to fill the ecological niches. The mammals, which were small and insignificant during the PETM, diversified dramatically in the aftermath, eventually giving rise to the primates and ultimately to us. The PETM reshaped the biosphere, but it didn't end life. Earth recovered. If an industrial civilization collapsed 55 million years ago due to runaway climate change, and if the PETM was the result, Earth would recover just as it did from the real natural PETM. Life would go on. New species would evolve, and 55 million years later, we'd be here, studying the sediments, finding evidence of rapid warming and carbon injection, and attributing it to natural causes because that's the most parsimonious explanation, given what we know about Earth systems. This is a sobering thought. It suggests that even catastrophic industrial collapse might not leave unambiguous evidence over geological time. The planet heals, the biosphere adapts, and future civilizations would have no easy way to know what caused the disruption. Which raises the question, what would survive? If direct artifacts don't last and climate events can be mistaken for natural processes, what kind of evidence could actually prove a previous civilization existed? But before we answer that question, we need to understand something crucial about Earth's climate history. The P10 wasn't unique, it was part of a pattern. The Paleocene-Eocene thermal maximum stands out because it's been studied so intensively, but it's not the only mysterious climate event in Earth's history. The geological record is punctuated with sudden temperature spikes, carbon cycle disruptions, and mass extinctions that still puzzle scientists. Each one raises the same uncomfortable question: could any of these be technological fingerprints rather than natural catastrophes? Consider the Torsion Ocean anoxic event, which occurred about 183 million years ago during the early Jurassic period. Ocean temperatures spiked, oxygen levels in the deep ocean plummeted, and marine life suffered catastrophic losses. The extinction wasn't as severe as the end Permian or end Cretaceous mass extinctions, but it was significant enough to reshape marine ecosystems. Black shales from this period, rich in organic carbon, suggest that ocean waters became stagnant and oxygen depleted across vast areas. The cause? Volcanic activity is the leading suspect, specifically massive eruptions in the Karoo-Ferrar Large Igneous Province, which covered parts of southern Africa and Antarctica with flood basalts. These eruptions would have released enormous quantities of carbon dioxide and sulfur into the atmosphere, triggering rapid warming and ocean acidification. The geochemical evidence supports this interpretation. There are ash layers coinciding with the carbon isotope excursion. Rare earth element patterns suggest volcanic input. Everything points to a natural catastrophe. But here's where it gets interesting. The carbon released during the torsion event occurred in multiple pulses over about 500,000 years. There wasn't a single massive injection, but rather repeated episodes of carbon input, each followed by partial recovery before the next pulse. This creates a sawtooth pattern in the isotope record, and that pattern could theoretically be produced by industrial activity that waxed and waned over time, perhaps as different regions industrialized or as resources were depleted and new ones discovered. Now, to be clear, there's no reason to invoke industrial civilization for the torsion event. The volcanic explanation is perfectly adequate and supported by multiple lines of evidence, but the example illustrates how even complex multi-phase climate disruptions can arise from natural causes. If you found a similar pattern in a poorly preserved section of rock from 300 million years ago, with no volcanic ash layers, no clear geological context, just a carbon isotope record showing repeated disturbances, how confident could you be about its cause? Or consider the Aptian Ocean anoxic event, roughly 120 million years ago during the Cretaceous period. This was another episode of global ocean oxygen depletion lasting about 1 million years. Carbon burial was so intense during this period that it formed many of the world's petroleum source rocks. The black shales deposited during the Aptian OAE are now major oil reservoirs in places like the Middle East, West Africa, and South America. In a very real sense, the oil we burn today is the fossilized remnant of that ancient environmental catastrophe. Again, the trigger appears to be volcanism, this time from the Ontong Java Plateau in the Pacific Ocean, one of the largest volcanic events in the past 200 million years. Millions of cubic kilometers of basalt erupted underwater, covering an area the size of Alaska. The volcanic gases altered ocean chemistry. The increased nutrient runoff from intensified weathering fed massive algal blooms, and the combination created anoxic conditions that persisted for 1 million years. But imagine you're a geologist 100 million years in the future, and you've forgotten about the Ontong Java Plateau. You're looking at black shales rich in organic carbon, with carbon isotope values indicating massive carbon cycle disruption. You see evidence of enhanced weathering, suggesting increased rainfall and runoff. You find traces of elevated metal concentrations that could indicate either volcanic input or industrial pollution. Without the full geological context, without the ability to map the extent of flood basalts and correlate them precisely with the timing of the anoxic event, could you be certain this wasn't the result of industrial activity? The answer should be yes, because there are other lines of evidence. The sheer scale of the event affecting all the world's oceans simultaneously suggests something bigger than even the largest conceivable industrial civilization could manage. The duration, 1 million years, is too long for industrial activity, which by definition is energetically intense, and would either collapse or transition to something more sustainable within thousands of years, not millions. And the gradual recovery, showing slow oxygenation as volcanic activity waned, fits natural processes better than technological collapse. But these certainties depend on having good geological preservation, extensive geographical coverage, and detailed temporal resolution. Strip away some of that data quality, as inevitably happens with older rocks, and the interpretation becomes less clear-cut. There's an even more dramatic example from deeper time: the end-Permian mass extinction, about 252 million years ago. This was the greatest extinction event in Earth's history, killing an estimated 90 to 96% of all marine species and 70% of terrestrial vertebrate species. The world was devastated on a scale that makes the asteroid impact that killed the dinosaurs look mild by comparison. The trigger, once again, appears to be volcanism, specifically the Siberian Traps, a massive flood basalt province that covered millions of square kilometers of what is now Russia. The eruptions lasted for hundreds of thousands of years, pouring out enough lava to bury an area the size of the continental United States under a kilometer of basalt. The environmental effects were catastrophic: rapid global warming, ocean acidification, anoxia in the seas, acid rain on land, possibly even ozone layer depletion from volcanic chlorine. But here's something worth considering. The end-Permian extinction didn't happen all at once. There were multiple pulses of extinction over perhaps a million years or more. Some groups of organisms went extinct early, others survived longer before succumbing. The recovery took 5 to 10 million years, far longer than for any other mass extinction. And during the recovery period, ecosystems were dominated by disaster taxa, opportunistic species that thrive in disturbed environments but give way to more diverse communities once conditions stabilize. This complex multi-phase pattern has led some researchers to propose that the Siberian Traps volcanism, while certainly the main driver, wasn't the only factor. Perhaps the initial warming triggered feedback loops, releasing methane from seafloor hydrates or from Arctic permafrost, creating a cascade of climate disruptions that persisted long after the eruptions ended. Perhaps wildfires, ignited by volcanic activity or lightning in the oxygen-rich late Permian atmosphere, consumed huge swaths of vegetation, adding carbon to the atmosphere and destroying ecosystems that might otherwise have provided refuges for struggling species. None of this requires invoking industrial civilization. The end-Permian mass extinction is thoroughly explained by natural catastrophic volcanism and its consequences. But imagine you're examining a similar event from 500 million years ago, or 700 million years ago, in rocks that have been metamorphosed and eroded, with only fragmentary fossil preservation. You find evidence of rapid warming, carbon cycle disruption, and mass extinction. You can't find the volcanic source because it's been subducted or eroded away. How do you interpret what you're seeing? The honest answer is that you do your best with the evidence available, you propose the most parsimonious explanation, and you remain open to revision as new data emerges. And most of the time, the most parsimonious explanation is natural catastrophe, not technology, because we know volcanism and climate change have happened repeatedly throughout Earth's history, while we have exactly one example of industrial civilization. But the Silurian Hypothesis asks us to consider the possibility, however remote, that we might be wrong. Not because there's evidence we're wrong, but because the nature of geological preservation means that certain kinds of evidence might not survive to be found. This is intellectually honest. It's acknowledging the limits of inference from incomplete data. And there's one more category of climate anomaly worth discussing: snowball Earth events. These are periods when Earth's surface froze over, possibly completely, with ice extending from the poles to the equator. The geological evidence for these events is strong, including glacial deposits at tropical latitudes, sedimentary features consistent with glacial melt, and distinctive cap carbonates that formed when the ice melted and weathering accelerated. The most severe snowball Earth episodes occurred between 720 and 635 million years ago, during the Cryogenian period of the Neoproterozoic. For tens of millions of years, Earth was a frozen ball, with ice possibly a kilometre thick covering the oceans. Life survived, probably in refuges around volcanic hotspots or in ice-free pockets, but it must have been touch and go. When the ice finally melted, perhaps triggered by volcanic CO2 building up in the atmosphere over millions of years until greenhouse warming overwhelmed the ice albedo feedback, the world experienced a dramatic climate whiplash, swinging from extreme cold to extreme heat. Could industrial civilization cause a snowball Earth event? It seems unlikely. Industrial activity warms the planet through greenhouse gas emissions, not cools it. But there are speculative scenarios. If a civilization developed advanced geoengineering and tried to combat warming by increasing Earth's albedo, reflecting more sunlight back to space, they might overshoot and trigger runaway cooling. Injecting sulfate aerosols into the stratosphere, a proposed technique for solar radiation management, could cool the planet if done excessively, or if civilization collapsed after deploying such aerosols, the cooling might persist and intensify. This is wildly speculative, and there's absolutely no evidence that snowball Earth events were anything other than natural climatic excursions, probably related to continental configurations, volcanic activity, and feedback loops in Earth's climate system. But the point is that even extreme climate events, ones that seem far outside the range of what technology could produce, might theoretically have technological causes under the right circumstances. The takeaway from all these climate anomalies is that Earth's history is full of dramatic events. Volcanic eruptions, asteroid impacts, orbital variations, ocean circulation changes. All of these have shaped climate and life over billions of years. Most of the time we can identify the causes with reasonable confidence. But occasionally, especially in older, poorly preserved sections of the rock record, we're left with mysteries. And the Silurian Hypothesis reminds us that one of the possible explanations, however unlikely, is technological activity by a previous civilization. This doesn't mean we should jump to that conclusion. Extraordinary claims require extraordinary evidence, and there's no extraordinary evidence for previous civilizations. What it means is that we should be humble about the limits of our knowledge, careful about our assumptions, and willing to consider alternative hypotheses even if they seem far-fetched, as long as we evaluate them honestly against the available data. With that context established, we can now return to the central question: what would actually survive from an ancient industrial civilization? Let's conduct a thought experiment. Imagine that modern human civilization collapses tomorrow. Maybe nuclear war, maybe pandemic, maybe climate catastrophe, doesn't matter. Humans are reduced to a small population of survivors who revert to hunter-gatherer lifestyles. Over time, even those survivors die out or evolve into something else. 10 million years pass. 20 million, 50 million. An intelligent species, perhaps evolved from some other lineage, rediscovers technology, develops science, and begins studying Earth's past. What evidence of us would they find? Start with the obvious stuff. Cities, roads, buildings all gone. Erosion would level them within thousands of years. Metal would rust, concrete would crumble, glass would dissolve. Within 100,000 years, virtually no surface structures would remain recognizable. Deep infrastructure might last longer. Subway tunnels, mines, deep foundations for skyscrapers. These could theoretically survive if they're in geologically stable regions. But even these would eventually collapse, fill with sediment, be deformed by tectonic activity. After millions of years, they'd be anomalies, ambiguous features that could be mistaken for natural caves or sediment channels. What about in orbit? Satellites and space debris orbit Earth, and in the vacuum of space they don't corrode like they would on the surface. But orbital mechanics are unforgiving. Objects in low Earth orbit experience atmospheric drag, however slight, which causes their orbits to decay. Within centuries, most satellites would have fallen back to Earth and burned up in the atmosphere. Objects in higher orbits, particularly in geostationary orbit, might last longer, but over millions of years, even these would be perturbed by the Moon's gravity, by solar radiation pressure, by interactions with Earth's magnetic field, until they too spiral away or crash. The Moon is a different story. The Moon has no atmosphere, no weather, no tectonic activity. Footprints left by Apollo astronauts will remain visible for millions of years, possibly billions, until micrometeorite bombardment gradually erases them. Hardware left on the lunar surface, descent stages of lunar modules, rovers, flags, those might survive much longer than anything on Earth. But they're tiny objects on a huge surface. And finding them without knowing where to look would be incredibly difficult. A future species searching the Moon for evidence of ancient civilization would need to scan vast areas with high-resolution imaging. And even then, they might miss the Apollo sites entirely. Mars is similar. Less atmosphere than Earth, no plate tectonics, so artifacts would last longer. The rovers we've sent to Mars, Curiosity, Perseverance, these machines will sit on the Martian surface for geological ages unless buried by dust storms. But again, finding them would require systematic surveying. Frank and Schmidt suggest that future scientists looking for evidence of a prior civilization should consider extraplanetary locations precisely because preservation is better. If you can't find anything on Earth, check the Moon, check Mars, but that's a harder search, requiring technology we don't yet have. So if physical artifacts don't survive, what does? The answer is chemistry. Specific molecules, specific isotopes, specific chemical signatures that are uniquely artificial and couldn't be produced by natural processes. The challenge is finding ones that last. Plastics are a prime example, and they've received considerable attention as potential markers of the Anthropocene, the proposed geological epoch defined by human impact on the planet. We produce about 300 million tons of plastic every year, roughly equivalent to the weight of the entire human population. Much of this ends up in the oceans, where it breaks down into microplastics, tiny particles less than 5 millimeters across. These microplastics are being incorporated into marine sediments right now, creating a layer that future geologists could theoretically detect. Recent studies have shown that microplastic abundance in sediment cores tracks the growth of plastic production over the past 70 years. You can literally see the spike beginning in the 1950s, when mass production of plastics began, rising exponentially to the present. This creates a clear stratigraphic marker, a plastic layer that could identify the Anthropocene in the geological record. But there's a catch. Plastics degrade over time. Ultraviolet light breaks polymer chains. Bacteria are evolving to consume plastic, albeit slowly. Heat and pressure during diagenesis, the transformation of sediment into rock, can alter or destroy plastic molecules. Studies of sediment cores show that plastics are preserved better in undisturbed deep ocean sediments than in shallow coastal areas where mixing and biological activity are higher. But even in the best conditions, after tens of millions of years, the distinctive molecular structure of synthetic polymers might be sufficiently degraded that identifying them as artificial becomes ambiguous. There's also a paradox here. The more sustainable and environmentally friendly a civilization becomes, the less evidence it leaves. If we transition away from plastic to biodegradable materials, if we shift to renewable energy, if we minimize our chemical footprint, future geologists would have a harder time detecting us. A civilization that existed for thousands of years using entirely sustainable technology, solar panels, wind turbines, organic materials, such a civilization might leave almost no trace. Ironically, the worst civilizations, the ones that trash their planet with pollution and waste, are the most detectable. This is not an encouraging thought. Nuclear isotopes are another possibility, but as we discussed earlier, most have half-lives too short to survive geological time. The exception is uranium and its decay products. Nuclear power plants and weapons testing create distinct isotopic signatures in uranium and plutonium that differ from natural ratios. If a civilization used nuclear energy on a large scale, these signatures might be detectable millions of years later. But you'd need to find exactly the right place to look, perhaps in sediments deposited near nuclear waste repositories or weapons testing sites. There's a natural analogue that's worth mentioning. In Oklo, Gabon, there's a uranium deposit that spontaneously underwent nuclear fission reactions about 2 billion years ago. Groundwater flowing through the uranium ore moderated the reactions, creating a natural nuclear reactor that operated intermittently for hundreds of thousands of years. The isotopic signatures left by these reactions are still detectable today. They're weird, anomalous, clearly not normal uranium. When they were first discovered in the 1970s, scientists briefly wondered if they might be evidence of ancient nuclear technology before realizing it was a natural phenomenon. This demonstrates that nuclear signatures can survive geological time, but it also shows that natural processes can mimic technological ones. Distinguishing between them requires careful analysis. Chemical fertilizers might leave a signature. Modern agriculture uses massive amounts of synthetic nitrogen compounds. Nitrogen isotope ratios in sediments could theoretically record this, but nitrogen is mobile, and isotope ratios can be altered by biological processes and diagenesis. After millions of years, the signal would be weak and ambiguous. One of the more intriguing possibilities is rare earth elements. Modern technology uses rare earth metals in everything from electronics to catalytic converters. These elements are naturally rare, but technology concentrates them. A sudden spike in rare earth element concentrations in sedimentary layers might indicate industrial activity, but again, you'd need the right preservation conditions and the right analytical techniques to detect it. The bottom line is that detecting an industrial civilization from millions of years ago would require a combination of evidence. You'd want chemical anomalies, isotopic excursions, sedimentary changes, possibly even morphological features in the fossil record if the civilization modified organisms through breeding or genetic engineering. Multiple independent lines of evidence, all pointing to the same conclusion, all preserved in the right place at the right time, is not impossible, but it's very, very difficult. And there's one more twist to consider, one that Frank and Schmidt emphasize. The more advanced and sustainable a civilization becomes, the less evidence it leaves. This creates a paradox, but before we explore that paradox, there's another category of evidence worth examining. Large-scale modifications to Earth's surface that might survive even when artifacts don't. When we think about the lasting impact of human civilization, we often imagine buildings and monuments, the pyramids of Egypt, the Great Wall of China, Angkor Wat. These structures have persisted for thousands of years and might last for tens of thousands more, with some recognizable features. But millions of years? Not a chance. Weathering, erosion, tectonic forces all would reduce them to unrecognizable rubble, and even that rubble would eventually be ground down and dispersed. Yet, there are some human modifications to Earth's surface that might leave detectable traces for much longer. Not because the structures themselves survive, but because they alter geology in ways that persist. Think about quarries and mines. Modern civilization has excavated enormous volumes of rock and earth. Open-pit mines can be kilometers across and hundreds of meters deep. The Bingham Canyon mine in Utah, one of the world's largest, is 4 kilometers wide and over 1 kilometer deep. That's a hole you could see from space. If humans disappeared tomorrow and geological processes were allowed to run their course, what would happen to that hole? Initially, weathering and erosion would begin filling it in. Landslides from the walls would dump material into the pit. Streams would carry sediment. If sea level rose and the area was flooded, marine sediments would accumulate. Over hundreds of thousands of years, the hole would fill. But here's the key. The infilling sediments would be geologically anomalous. They'd be younger than the bedrock they're sitting in, creating a reverse stratigraphy that geologists could detect. The filled-in pit would show as a circular or irregular feature in cross-section, with jumbled, poorly sorted sediments that don't match the surrounding formation. Would this be recognizable as artificial millions of years later? Possibly. Natural processes can create similar features, things like sinkholes, collapsed lava tubes, or meteorite impact craters. But the chemical composition might be a clue. If the mine was extracting a specific mineral, say copper or gold, the tailings and spoil heaps would have concentrations of that mineral far exceeding natural background levels. Even after millions of years of weathering and dispersion, there might be geochemical anomalies detectable with the right analysis. Underground mines present a different challenge. Tunnels and shafts would collapse relatively quickly once maintenance stopped. Within centuries or at most a few millennia, most underground workings would be filled with rubble. But the voids would leave ghosts in the rock record. Collapsed zones, areas where the rock has subsided or fractured, might remain detectable. And if the mine flooded and minerals precipitated from groundwater, you might get unusual mineral deposits filling the old workings. There are natural analogues that show how persistent such features can be. The Oklo natural nuclear reactors in Gabon, which we mentioned earlier, are 2 billion years old, and geologists can still identify the exact zones where fission occurred. The rock in those zones has been altered by heat and radiation, and the uranium isotope ratios are anomalous. If natural nuclear reactions can leave detectable traces for 2 billion years, could artificial mines leave traces for a few 100 million? The answer is maybe, under the right conditions. If the mine was in a geologically stable region, if it wasn't subjected to extreme metamorphism or erosion, if it remained buried and protected, it might leave a signature. But these are big ifs. Most of Earth's surface gets recycled on timescales of hundreds of millions of years. Continental drift, subduction, mountain building, all of these processes destroy or radically alter old features. The odds of a specific mine site surviving long enough to be discovered by a future civilization are not good. What about dams and reservoirs? Modern humans have built thousands of large dams, creating artificial lakes that trap sediment. When a river is dammed, sediment that would normally flow downstream gets deposited in the reservoir. This creates a distinct sedimentary sequence, rapid accumulation behind the dam, with fine-grained material settling out in still water, creating varved deposits similar to lake sediments. Downstream of the dam, sediment deposition decreases because the river is carrying less sediment. If the dam failed or was abandoned, the reservoir would drain and erosion would begin cutting through the accumulated sediments. But for a time, there would be an anomalous sedimentary package, very thick accumulation in one location with a sharp boundary at the former dam site. Could this be detected millions of years later? It's doubtful. Rivers naturally migrate and change course over geological time. Lakes form and drain for all sorts of natural reasons. An old reservoir would be hard to distinguish from a natural lake that existed briefly and then disappeared. Unless you found the dam itself, or rather the pile of rubble that used to be the dam, you'd have no reason to interpret the sediments as artificial. Landfills are another intriguing possibility. Modern civilization produces massive quantities of waste, and much of it ends up in landfills, compacted and buried. A large landfill might contain hundreds of thousands of tons of material: plastics, metals, glass, organic waste, construction debris, all mixed together in concentrations and combinations that don't occur naturally. Over time, this material would be buried more deeply as sediment accumulated on top. The organic waste would decay, producing methane that might escape or be trapped. The metals would corrode, the plastics would degrade. But the overall chemical signature would be weird. Elevated concentrations of heavy metals, synthetic organic compounds, glass particles, all in a relatively thin localized layer. This might be recognizable as anomalous even millions of years later. There's a modern analogue, though on a much smaller scale. Archaeologists excavating ancient settlements find trash heaps, middens, that are chemically distinct from natural sediments. Elevated phosphorus from food waste, ash from fires, fragments of pottery and tools. These features can be detected thousands of years after they were deposited. A modern landfill would be like a super midden, packed with materials that scream artificial. But again, you'd need the right preservation conditions. If the landfill was in an area that became tectonically active, or if it was eroded away, or if it was subducted and melted, the evidence would be destroyed. And even if it survived, would future geologists recognize it for what it was? Or would they interpret it as some kind of natural concentration mechanism, a weird geological fluke? Then there are modifications to river systems and coastlines. Humans have straightened rivers, dredged channels, built harbours and breakwaters, reclaimed land from the sea. These activities create artificial landforms that might leave traces. A straightened river channel cuts through terrain in a way that natural meandering rivers don't. Harbour jetties create sediment accumulation patterns that differ from natural beach processes. Detecting these features millions of years later would require extraordinary luck and careful analysis. You'd need to find a region where the ancient shoreline or river system was preserved, which means it was buried and protected but not destroyed. You'd need to recognise that the geometry of the features is unnaturally regular or aligned in ways that natural processes don't produce. And you'd need to rule out all the natural processes that can create similar patterns. Coastlines are particularly tricky because sea level has fluctuated dramatically over Earth's history, and tectonic activity constantly reshapes them. An ancient harbour would be either underwater, uplifted into mountains, or eroded away. The chances of it being preserved in a recognisable form are slim. What about really large-scale modifications? Some scientists and engineers have proposed geoengineering projects that would alter Earth at continental or global scales, painting roofs white to increase albedo, deploying massive arrays of mirrors in space to reduce solar radiation reaching Earth, fertilizing oceans with iron to stimulate carbon-fixing plankton blooms. These interventions might leave traces. Iron fertilization, for instance, would create anomalous sediment layers with elevated iron concentrations and increased organic carbon burial. But distinguishing this from natural iron deposition, perhaps from increased weathering during a warm, rainy period, would be challenging. You'd need to show that the iron was deposited in patterns inconsistent with natural ocean circulation and weathering. Space-based mirrors or solar shades wouldn't leave direct evidence on Earth, but they might be detectable in orbit. Defunct satellites and debris in geosynchronous orbit, a about 36,000 kilometers above Earth's equator, are effectively in stable positions that could persist for millions of years. Future civilizations with space capabilities could detect them with orbital surveys, but from Earth's surface with no space program, you'd never know they were there. Perhaps the most intriguing possibility for detecting ancient megastructures isn't on Earth at all, but in the way they might have altered Earth's orbit or rotation. This is highly speculative, but some proposed geoengineering schemes involve moving asteroids to alter Earth's orbit slightly, changing the amount of solar radiation received. Or they might involve redistributing mass on Earth's surface in ways that affect the planet's moment of inertia and thus its rotation rate. These changes would be incredibly subtle and would likely be erased by natural processes over millions of years. Earth's rotation is gradually slowing due to tidal friction with the Moon, and its orbit undergoes natural variations due to gravitational interactions with other planets. Teasing out an artificial signal from these natural variations would be nearly impossible without detailed models and extensive data, neither of which we have for the distant past. The search for ancient megastructures, then, comes down to looking for geological anomalies that are hard to explain by natural processes alone. And that's a high bar, because nature is creative and produces all sorts of weird features. Geologists have a saying, the most important phrase in science is not eureka, but that's funny, followed by a lot of careful investigation. When you find something strange, you don't immediately conclude it's artificial. You look for natural explanations first, and only when all reasonable natural explanations have been exhausted do you consider more exotic possibilities. In the case of the Silurian Hypothesis, there are no geological anomalies that require invoking ancient industrial civilizations. Everything we see can be explained by natural processes, but the hypothesis serves as a reminder to remain open-minded, to keep looking, to not assume that absence of evidence means we've looked everywhere we need to look. With physical evidence on Earth so difficult to detect, it's worth considering whether evidence might be better preserved elsewhere. Here's an uncomfortable irony buried in the Silurian Hypothesis. The civilizations we'd be most likely to detect are the ones that failed most catastrophically. Industrial societies that burned massive quantities of fossil fuels, pumped pollutants into the atmosphere and oceans, created mountains of non-biodegradable waste. These are the civilizations that would leave the clearest signatures in the geological record. Their excess, their waste, their environmental destruction becomes their unintended monument. Conversely, a civilization that achieved sustainability, that transitioned to renewable energy, that managed its waste carefully, that minimized its chemical footprint, such a civilization would be nearly invisible to future geologists. Solar panels and wind turbines don't require mining carbon from deep underground and spewing it into the atmosphere. They don't produce unique isotopic signatures. They don't generate vast quantities of persistent synthetic molecules. A purely solar civilization might exist for thousands of years and leave less trace than our current industrial culture will leave in 2 centuries. This creates a perverse selection effect. If there were multiple industrial civilizations in Earth's past, we'd be most likely to detect the failures and least likely to detect the successes. The wise civilizations that achieved balance with their environment would pass through geological time like ghosts, leaving barely a whisper. The foolish civilizations that overshot their resources and collapsed in pollution and climate chaos would leave chemical scars that persist for millions of years. What does this tell us? For one thing, it suggests that the absence of evidence for previous civilizations might not mean much. We might be surrounded by the remnants of wise, sustainable societies and simply not recognize them because they were careful about their impact. The only previous civilizations we could reliably detect would be ones that made similar mistakes to ours, ones that industrialized rapidly, exploited fossil fuels, and altered their climate before either collapsing or transitioning to sustainability. There's a grim thought buried in this. If we find evidence of a previous industrial civilization in the geological record, it would probably mean we're looking at the chemical signature of their collapse. Climate change markers, ocean acidification, mass extinction. The evidence would be cautionary, a warning written in stone. This is what happens when industrial civilization loses control. But we might also take some comfort in the sustainability paradox. If we manage to transition away from fossil fuels, if we clean up our pollution, if we achieve a steady-state civilization that can persist for millennia without destroying the biosphere, then future geologists 100 million years from now might not find clear evidence of us either. They might see a brief anomaly in the sediment record, a strange blip in carbon isotopes and plastic concentrations, followed by a return to more natural conditions. And they might wonder what caused the blip. Natural event? Brief industrial pulse? They might never know for sure. There's something both humbling and hopeful in that possibility. Humbling because it means our grand civilization, all our achievements and struggles, might compress down to an ambiguous layer in the rock record, a puzzle for future scientists who will never fully understand what we were. Hopeful because it means sustainable civilization is possible, that we can exist without leaving catastrophic permanent scars, that the path forward isn't inevitably toward collapse and extinction. The Silurian Hypothesis forces us to think about our legacy not in terms of monuments and ruins, but in terms of chemistry and climate. What mark are we leaving on the planet? What will future beings, whether evolved from us or from some other lineage, think when they study the sediments from our time? Will they see evidence of intelligence and wisdom, or just a brief flare of combustion followed by silence? These questions become even more pointed when we consider that Earth might not be the only place to look for evidence of previous civilization. There's a fascinating suggestion buried in Schmidt's paper, one that expands the scope of the hypothesis beyond Earth's surface. If you want to find evidence of ancient civilization, don't just look at terrestrial sediments. Look at places where erosion is minimal and preservation is better. Look at the Moon. Look at Mars. The Moon is geologically dead. No atmosphere means no weather, no wind, no rain to wear things down. No tectonic activity means the surface doesn't get recycled. No liquid water means no chemical weathering. Things just sit there, accumulating dust from micrometeorite impacts, but otherwise remaining unchanged. The Apollo astronauts left footprints in the lunar regolith in 1969, and those footprints will still be visible millions of years from now. The descent stages of the lunar modules, the rovers, the flags, all of that hardware will persist essentially forever, unless directly struck by a meteorite or buried by a landslide. If an ancient civilization had space capability, even rudimentary space capability, they might have left artifacts on the Moon, a crashed probe, a landing site, debris from a failed mission. These artifacts would be far better preserved than anything on Earth. The challenge is finding them. The Moon's surface area is about 38 million square kilometers. That's enormous. Scanning it all with sufficient resolution to detect small artifacts would require a comprehensive lunar survey, something we haven't done and won't do anytime soon, but it's theoretically possible. Future lunar missions, either crewed or robotic, could include archaeological surveys as part of their scientific objectives. High-resolution orbital imaging could identify anomalous features, unnatural shapes or compositions that might indicate artificial objects. Then targeted surface missions could investigate. It sounds like science fiction, and maybe it is, but it's not physically impossible. If there were artifacts on the Moon from a previous civilization, we could find them if we looked hard enough. Mars is similar but more complicated. Mars has an atmosphere, thin but present, which means there is some weathering. Dust storms can bury features, but there's no plate tectonics, and liquid water is rare, so erosion is much slower than on Earth. A structure on Mars could last for hundreds of millions of years, possibly longer if it's in a protected location. The rovers we've sent to Mars will be detectable for geological ages. They're made of metal and plastic, materials that degrade slowly in the Martian environment. Future Martian archaeologists, whether human colonists or some other species, could theoretically find curiosity or perseverance millions of years after they stopped functioning. Again, the challenge is search area. Mars is big. It has roughly the same land surface area as Earth's continents, about 145 million square kilometers. Looking for small artifacts in that expanse would require systematic surveying. But if a previous earthly civilization had reached Mars, if they'd established bases or conducted missions, they might have left larger structures that would be easier to spot. There's an even more speculative possibility. If a previous civilization existed and achieved spaceflight, they might have established industrial facilities in orbit or on asteroids. Space is a great place for certain types of manufacturing because you have vacuum, microgravity, abundant solar energy, and access to raw materials from asteroids. Artifacts in space, in stable orbits beyond Earth's immediate vicinity, could persist for billions of years, but finding them would require surveying vast volumes of space, detecting small objects among the cosmic debris. The point of all this is that the Silurian hypothesis isn't limited to Earth's geological record. If you take seriously the possibility of previous industrial civilization, you should also take seriously the possibility that they went to space. And if they did, the evidence might be up there rather than down here. This expands the hypothesis into a much broader question about the persistence of technological civilizations across solar system scales. It also has implications for the search for extraterrestrial intelligence and for how we think about exoplanets. One of the reasons Frank and Schmidt developed the Silurian hypothesis was to think about how we detect industrial civilizations on exoplanets. The same challenges that make it hard to detect ancient civilizations on Earth apply, perhaps even more severely, to distant planets. Current techniques for studying exoplanets rely on spectroscopy, analysing the light that passes through a planet's atmosphere to determine its chemical composition. If you detect oxygen and methane together, that might indicate biology because those gases react with each other and would normally not coexist unless something is actively producing them. If you detect industrial pollutants, artificial chemicals that don't occur naturally, that would be a biosignature, potentially a technosignature, evidence of technological civilization. But here's the problem. Those signatures are detectable only while the civilization is actively producing them. If an industrial civilization existed on an exoplanet 50 million years ago and then went extinct, their atmospheric pollution would have been scrubbed away by natural processes long before we turned our telescopes in that direction. We'd see a normal planet with normal atmospheric chemistry, and we'd conclude it has no current technological civilization, which would be correct, but we'd miss the fact that it had one in the past. This creates a temporal bias in our search for extraterrestrial intelligence. We can only detect civilizations that exist right now, at the exact moment we're looking. Civilizations that existed in the past or will exist in the future are invisible to us. This dramatically reduces the probability of detection. Space is vast, and the timescales for civilizations to arise and fall might be brief compared to the billions of years planets exist. The chances that we happen to be looking at an exoplanet at exactly the moment it has a detectable civilization are small. The Silurian hypothesis suggests we should think about long-term markers, things that persist even after active civilization ends, geological or atmospheric signatures that take millions of years to erase, artificial structures in space or on moons, changes to the planet's surface that might be detectable from orbit. These are harder to detect than atmospheric technosignatures, but they have longer persistence and thus a better chance of being found. There's also the possibility of self-replicating probes. If a civilization wants to explore the galaxy but can't send living beings because of the distances involved, they might send robotic probes that can reproduce themselves using local resources. These probes could spread through the galaxy over millions of years, reaching every star system, including ours. If such probes exist, we might find them in our own solar system, perhaps dormant on asteroids or moons, waiting to be reactivated. This is speculative, but it's a logical extension of thinking about how technological civilizations might leave persistent traces. Frank and Schmidt's work has influenced astrobiology by encouraging scientists to think more carefully about timescales and preservation. It's not enough to look for current signs of life or technology. We should also think about how to detect past civilizations, how to recognize the remnants of industrial activity in geological or astronomical records. This requires new techniques, new ways of analysing data, new assumptions about what counts as evidence, and it raises profound questions about the Fermi paradox, the puzzle of why we haven't detected alien civilizations despite the apparent probability that they should exist. Maybe we have detected them, or their remnants, and just didn't recognise it. Maybe the galaxy is full of dead civilizations, ones that rose, industrialised and fell, leaving traces we haven't learned to read yet. Or maybe civilizations are rare, and we're one of the first, exploring a cosmos not yet crowded with intelligence. The Silurian hypothesis doesn't answer these questions, but it sharpens them. It forces us to think about what detection means, what evidence looks like, what assumptions we're making about the persistence of technological signatures, and in doing so, it changes how we think about our place in the universe. But perhaps the most important thing to remember about the Silurian hypothesis is what Frank and Schmidt actually believe. It's time to be clear about something. Adam Frank and Gavin Schmidt do not believe that an industrial civilization existed on Earth before humans. They've stated this explicitly and repeatedly. The opening of their paper includes this passage. While we strongly doubt that any previous industrial civilization existed before our own, asking the question in a formal way that articulates explicitly what evidence for such a civilization might look like raises its own useful questions. This is crucial. The Silurian hypothesis is not a claim, it's a thought experiment. It's a way of exploring the limits of our knowledge and the nature of evidence in the geological record. By asking, could we detect an ancient industrial civilization? They're not suggesting one existed. They're using the question as a tool to investigate how well we understand Earth's past, and how we might search for technological civilizations elsewhere. Frank has been particularly emphatic about this in interviews. He's said that the hypothesis is valuable precisely because it forces scientists to articulate what they would look for and how confident they could be in their interpretations. It's easy to assume we'd know if there had been a previous civilization. The Silurian hypothesis challenges that assumption and shows that detection would be far more difficult than people intuitively expect. This is how science works. You ask uncomfortable questions, you challenge assumptions, you explore hypothetical scenarios not because you believe them, but because doing so reveals gaps in your understanding. The Silurian hypothesis has been valuable because it's prompted serious discussion about geological preservation, about how industrial activity manifests in sedimentary records, about the timescales over which evidence persists. It's also sparked some interesting research. Scientists have looked more carefully at chemical signatures that might indicate industrial activity. They've thought about what the Anthropocene will look like to future geologists and what markers might be most reliable. They've considered how diagenesis affects the preservation of synthetic materials. All of this work is scientifically useful regardless of whether you think there was actually a previous civilization. There's been some misunderstanding in popular discussions of the hypothesis. Some people have seized on it as support for ancient astronauts or lost advanced civilizations. Reading into it claims that Frank and Schmidt never made. This is frustrating for the scientists involved because it misrepresents their work. They're not promoting pseudoscience. They're doing rigorous, peer-reviewed science that happens to involve an intriguing hypothetical. The consensus in the scientific community is that there's no credible evidence for industrial civilizations predating humans on Earth. The geological record, despite its gaps, is detailed enough that a major industrial civilization would have left detectable traces. We would see anomalies in carbon isotopes, in chemical compositions, in fossil assemblages. We don't see those anomalies. The simplest explanation is that no such civilization existed. But the value of the Silurian hypothesis isn't in proving previous civilizations existed. It's in making us think carefully about what we mean by proof, what counts as evidence, what the geological record can and cannot tell us. It's a reminder that absence of evidence is not always evidence of absence, especially when the evidence is hard to preserve and we haven't looked everywhere we might look. It's also a reminder of how young we are, how brief our tenure on this planet has been, and how much of Earth's history we're still working to understand. 4.5 billion years is a long time. Humans have been here for an eye blink. What happened in all that time before us? We're piecing together the story from fragmentary evidence, making inferences, building models. The story we're constructing is probably mostly right. But it's worth remembering that it's incomplete and always subject to revision. The Silurian hypothesis fits into a tradition of thought experiments in science that illuminate by questioning. Einstein's thought experiments about riding a beam of light led to relativity. Schrödinger's cat illustrated the weirdness of quantum mechanics. The Silurian hypothesis illuminates the nature of geological evidence and the difficulty of detecting brief technological episodes in deep time. It's science fiction in service of science, and that's a valuable thing. We began this journey with a simple question. If an industrial civilization existed on Earth millions of years ago, would we know? And after exploring the geological record, the processes of fossilization, the chemistry of preservation, the challenges of detection, we can now offer an answer. We might not know. Depending on when this hypothetical civilization existed, how long it lasted, what technologies it used, and where its traces were preserved, we might be completely blind to its existence. This is not a comfortable conclusion for a species that prides itself on its knowledge and its mastery of the natural world. We like to think we understand Earth's history, that we've read the rock record and decoded its messages, and to a large extent, we have. The broad outlines of Earth's story are clear. The formation of the planet, the emergence of life, the evolution of complex organisms, the rise and fall of dinosaurs, the age of mammals, the appearance of humans. We know this story in remarkable detail, a testament to centuries of patient geological and paleontological work. But the Silurian hypothesis reminds us that there are limits to what we can know. The geological record is incomplete, fossilization is rare, direct evidence degrades, chemical signatures become ambiguous, and the further back in time you look, the less certain everything becomes. We're reading a history book with most of the pages torn out, trying to infer the plot from the fragments that remain. Does this mean we should take seriously the possibility that dinosaurs built cities? No, there's no evidence for that, and the burden of proof lies with anyone making such an extraordinary claim. What it does mean is that we should maintain appropriate humility about the completeness of our knowledge. We should be clear about what we know for certain, what we infer with confidence, and what remains speculation or unknown. The Silurian hypothesis is valuable because it makes this explicit. By asking the question in a rigorous scientific way, Frank and Schmidt have helped us understand the limits of geological detection. They've shown that brief technological episodes could theoretically occur and go undetected if they happened far enough in the past. They've identified what kinds of evidence might survive and what we should look for. And they've demonstrated that natural events can mimic technological signatures, making interpretation challenging. But perhaps the most profound contribution of the Silurian hypothesis is how it changes our perspective on our own civilization. We tend to think of industrial society as a permanent achievement, a new mode of existence that will persist indefinitely into the future. But geological thinking forces you to consider longer timescales. What will remain of our civilization in 10 million years? In 50 million? In 100 million? If we collapse, if we fail to achieve sustainability and our industrial society ends in catastrophe, future intelligent beings might find only the faintest traces of our existence. A thin layer of plastic microparticles in sediment, a brief carbon isotope excursion, perhaps some radioactive isotopes if they look in exactly the right place. They might puzzle over these anomalies, propose theories, debate whether they indicate natural events or technological activity, and they might never know for certain. Alternatively, if we succeed, if we transition to renewable energy and sustainable practices, if we manage to persist as a technological civilization for millions of years, we'll leave a different kind of mark. Not a catastrophic chemical scar, but a steady-state integration with the planet's natural systems. And paradoxically, that might be even harder to detect, because wise civilizations leave smaller footprints. This connects to something deeper. The Silurian hypothesis asks us to think about legacy. What mark do we want to leave? Do we want to be remembered, if we're remembered at all, as the civilization that burned through Earth's fossil carbon in a few centuries and then collapsed? Or do we want our legacy to be one of balance, of wisdom, of long-term thinking? The choice is ours, right now, in this critical century. We're at a hinge point in human history, where the decisions we make will echo through geological time. If we fail, future beings might study our layer in the rock record as a cautionary tale, a warning about the dangers of rapid industrialization without foresight. If we succeed, they might not notice us at all, which in some sense would be the highest compliment, evidence that we learned to live lightly on the planet we inherited. There's something both terrifying and liberating about the perspective the Silurian hypothesis offers. Terrifying because it shows how easily we could be forgotten, how brief and fragile our moment in time really is. Liberating because it frees us from the illusion of permanence, the idea that our current way of life is inevitable or eternal. Civilizations rise and fall. Geological time is patient. The planet will outlast us regardless of what we do. But that doesn't mean our choices don't matter. They matter intensely. To us, to the other species we share this planet with, to whatever future awaits. We might be the first civilization on Earth, or we might not. Either way, we won't be the last. Life will continue, evolution will continue, and someday, perhaps, another intelligent species will arise and ask the same questions we're asking now. But there's another dimension to this discussion that we haven't fully explored. What does the Silurian hypothesis tell us about the nature of intelligence, progress, and the meaning we assign to civilization itself? The Silurian hypothesis isn't just a scientific thought experiment, it's a philosophical meditation on impermanence, significance, and what we mean when we talk about progress. We humans have a deep-seated need to believe that what we do matters, that our accomplishments will be remembered, that we're building something that lasts. The idea that our entire civilization could vanish without a trace, that millions of years from now no one would even know we existed, this cuts against everything we tell ourselves about the importance of our lives and our works, but perhaps that's exactly the kind of humility we need. For most of human history, civilizations have risen and fallen on timescales of centuries or millennia. The Roman Empire seemed eternal to those living under it, but it collapsed. The Egyptian kingdoms persisted for thousands of years before fading into archaeology. The great cities of Mesopotamia, of the Indus Valley, of the Maya, all flourished and then were abandoned, buried under sand or jungle, forgotten until modern archaeologists rediscovered them. And yet, we found them. We excavated them. We deciphered their writing, studied their art, reconstructed their histories. These civilizations weren't truly forgotten because they existed recently enough, on a human timescale, that their traces remained accessible. A few thousand years is nothing geologically, barely enough time for significant erosion, nowhere near enough time for the rock record to swallow evidence completely. But push that timescale out to millions of years, and the equation changes. At that point, you're not just forgotten by historians, you're forgotten by the planet itself. The rock remembers nothing, or almost nothing, and what fragmentary traces remain are so ambiguous that they could be mistaken for natural phenomena. This is a different kind of forgetting, more absolute and final. Some people find this thought depressing. If nothing we build will last, if even memory of our existence will be erased by geological time, what's the point? Why try to achieve anything? Why not live for the moment and ignore the future? But that's the wrong lesson to draw. The Silurian Hypothesis doesn't say that what we do doesn't matter. It says that what we do matters now, to us, to the beings we share the planet with, to the generations that come immediately after us. The value of our actions isn't measured by whether they'll be remembered in 100 million years. It's measured by the lives we improve, the suffering we reduce, the beauty we create, the knowledge we discover in the here and now. There's a concept in Buddhist philosophy called anicca, impermanence. The understanding that all things change and nothing lasts forever. This isn't meant to be nihilistic. It's meant to free you from attachment to outcomes you can't control. You do what's right because it's right, not because you expect eternal reward or recognition. You build beautiful things knowing they'll decay. You love knowing you'll lose. And there's a kind of peace in that acceptance. The Silurian Hypothesis offers a cosmic version of anicca. Yes, your civilization will eventually be forgotten. Yes, the monuments you build will crumble. Yes, even the geological trace you leave will fade into ambiguity. But you exist now. Your choices have consequences now. The quality of those choices matters even if the record of them won't survive. This also changes how we think about progress. We often imagine progress as a linear march from primitive to advanced, from ignorant to knowledgeable, from weak to powerful. We assume each generation builds on the achievements of the previous one, adding to an ever-growing edifice of civilization. And certainly that's true on human timescales. We do build on previous knowledge. We do have more technology now than our ancestors did 1,000 years ago. But the Silurian Hypothesis reminds us that progress isn't guaranteed to be permanent. Civilizations can collapse. Knowledge can be lost. Technology can be forgotten. And on geological timescales, even successful, long-lasting civilizations eventually end. Either they transition into something so different that it's effectively a new civilization, or they go extinct, or they expand beyond their home planet and become something we wouldn't recognize. This doesn't mean progress is impossible or pointless. It means progress is local and temporary. A bubble of increased order and complexity in a universe that tends toward entropy and dissolution. That bubble can last for a long time by our standards, but it's still a bubble. Eventually it pops. What does this imply for how we should live? Perhaps it suggests we should focus on intrinsic goods rather than instrumental ones. An intrinsic good is something valuable in itself, not because it leads to something else. Beauty, knowledge, love, happiness. These are intrinsic goods. You pursue them because they make life better now, not because they'll pay off later. Instrumental goods are different. You pursue them as means to other ends. Money is instrumental. It's valuable because you can exchange it for things you actually want. Power is instrumental. It's useful because it lets you achieve your goals. Even technology is largely instrumental. We don't value smartphones for themselves, but for what they enable us to do. industrial civilization has become very focused on instrumental goods. We optimize for economic growth, technological advancement, power accumulation. We justify present sacrifices by appealing to future benefits. Work hard now so you can retire comfortably later. Pollute now so we can have economic growth that will eventually let us afford to clean up. Exploit resources now because future technology will find substitutes. But what if there is no later? At least not in the way we imagine. What if our civilization lasts another 1,000 years and then collapses, and no one remembers any of this? Then all those deferred goods, all those future benefits we sacrifice present well-being for, they never materialize. The only thing that was real was the present we lived through, and we made it worse in service of a future that didn't come. The Silurian Hypothesis suggests we should weight present well-being more heavily relative to future growth. We should ask whether our choices make life better now for actual beings who actually exist, not just whether they supposedly pave the way for some imagined glorious future. This doesn't mean ignoring the future entirely. We should still care about the world we're leaving for our children and grandchildren. But we should be skeptical of arguments that justify present harm for the sake of speculative long-term benefits that may never arrive. There's also something to be said about the value of awareness itself. Even if our civilization ultimately gets forgotten by the rock record, even if no future intelligence ever knows we existed, we know we existed. We're aware of the universe, capable of understanding it, able to feel wonder and awe at its scale and complexity. That awareness has value even if it's temporary. Carl Sagan captured this beautifully when he called humans a way for the cosmos to know itself. For billions of years, Earth existed without any being capable of understanding what it was, where it came from, how it worked. Rocks formed and eroded, continents drifted, life evolved, all without anyone watching or comprehending. Then, incredibly recently, consciousness emerged. And now the universe has, in us, a way to observe itself, to think about itself, to marvel at itself. That's extraordinary, regardless of how long it lasts. If human civilization collapses tomorrow and intelligence never re-evolves on Earth, the fact that it happened at all, that there were once beings who could contemplate deep time and ask whether they were first, that fact has intrinsic value. The universe was different because we were here. It was known for a brief moment in a way it wasn't before. And if we're not the first, if the Silurian Hypothesis is actually true, and there were previous intelligent species who also looked up at the stars and wondered about their place in the cosmos, then that's even more extraordinary. It would mean the universe has repeatedly given rise to consciousness, that this isn't a one-time fluke but a recurring phenomenon. We'd be part of a longer story, one episode in a series of civilizations rising and falling and being forgotten. There's something comforting in that possibility. It makes us less alone. Even if we never find evidence of previous civilizations, even if we can't communicate across the vast gulfs of time that separate us, we'd be connected by the simple fact of existence, by having faced similar questions and challenges, by having briefly illuminated the darkness before being swallowed by it again. The Silurian Hypothesis, then, is more than just a question about geological detection. It's a mirror we hold up to ourselves, asking what we value, what we hope for, what we fear. It's a thought experiment that reveals our assumptions about permanence, significance, and the meaning of our brief time on this ancient planet. And perhaps most importantly, it's a reminder that the questions we ask shape how we see the world, even when we can't definitively answer them. What will they find when they look back at us? What story will the rocks tell about this strange species that learned to split atoms and travel to other worlds, and nearly destroyed itself in the process? Will they see wisdom or folly, success or failure? The answer isn't written yet. We're still writing it day by day, choice by choice. The Silurian Hypothesis doesn't tell us what to do, but it does tell us to think carefully about the legacy we're creating, to consider timescales beyond our individual lives, or even our species' immediate future, to think geologically, to think cosmically, and maybe that's the real value of this hypothesis. Not whether it's true or false, not whether there really was a civilization before us, but the perspective it offers. The reminder that we're part of a much larger story, that Earth's history is vast and we're newcomers, that the rock record is both informative and humbling. We began by asking if we are the first civilization on Earth. The honest answer is, we don't know for certain, and we probably can't know with absolute certainty given the limitations of the geological record. But the question itself is valuable because it forces us to examine our assumptions, to understand the nature of evidence, to think about deep time and our place in it. If you found this exploration thought-provoking, if it changed how you think about Earth's history or humanity's future, hit that like button and subscribe. We're constantly exploring the boundaries of science, the questions that make us uncomfortable, the ideas that expand our perspective. The universe is full of mysteries, and our planet is full of them too, including mysteries buried in our own past. We may never know if we're the first, but we can choose what kind of civilization we'll be. We can choose whether to be wise or reckless, sustainable or destructive, memorable or forgettable. That choice is ours, and geological time is watching, patient and impartial, ready to record whatever we decide. The Silurian Hypothesis fundamentally challenges how we think about evidence and what we mean when we say we know something about the past. In everyday life, in historical studies, even in recent geological periods, we're accustomed to having relatively complete records. If you want to know what happened during the Roman Empire, you can read written accounts from Roman historians, examine archaeological sites with intact structures, analyze coins and pottery and tools. The evidence is abundant, clear, and relatively easy to interpret. Even for prehistoric times, for the period before writing, we have rich archaeological records from the last 10,000 or 20,000 years. We can excavate ancient settlements, examine stone tools in exquisite detail, extract DNA from bones, reconstruct diets from isotopic analysis of teeth, determine when and where crops were domesticated by studying ancient seeds. The evidence is fragmentary compared to historical periods, but it's still substantial and growing as archaeological methods improve. But extend that time frame from thousands of years to millions, and the nature of evidence transforms completely. We're no longer looking at individual objects and structures. We're looking at chemical signatures, isotopic ratios, statistical patterns in sediment compositions. We're inferring rather than directly observing. We're building models rather than reading documents. And critically, we're dealing with massive uncertainty. Consider how we know about past climates. For recent history, we have direct measurements, temperature records, rainfall data, atmospheric composition measurements from ice cores going back hundreds of thousands of years. These give us precise quantitative information about climate changes through the Pleistocene ice ages. We know, for instance, that during the last glacial maximum about 20,000 years ago, global average temperature was approximately 6 degrees Celsius cooler than today. Sea level was 120 meters lower because so much water was locked up in ice sheets. And atmospheric CO2 was around 180 parts per million. But what about climates from 100 million years ago? We don't have ice cores that old. Ice from that period has long since melted and refrozen countless times. Instead, we use proxy measurements. We look at oxygen isotope ratios in fossilized shells, which reflect temperature and ice volume. We examine plant fossils to infer what kinds of climates they lived in. We analyze sedimentary rocks to determine whether they were deposited in tropical versus temperate environments. We measure ratios of certain trace elements in microfossils that are sensitive to temperature. All of these proxies work, and when multiple independent proxies agree, we can be quite confident in our reconstructions. We know the Cretaceous period was much warmer than today, with no polar ice caps and tropical conditions extending to high latitudes. We know this from multiple lines of converging evidence. But the uncertainty is much larger than for recent climates. We might say the Cretaceous was 10 degrees Celsius warmer globally, but that number has error bars of plus or minus several degrees, and for brief climate excursions, events that lasted only thousands of years, the record gets fuzzy. We might miss them entirely if sediment accumulation was slow, or if the sediments from that time weren't preserved, or if we haven't looked in the right places. Now apply this same logic to detecting industrial civilization. What proxies would you use? You'd look for chemical anomalies, unusual concentrations of synthetic compounds, isotopic ratios that don't match natural patterns, elements present in combinations or quantities that require technological processes. You'd look for rapid changes in climate or atmospheric composition that might indicate massive fossil fuel burning. You'd look for extinction patterns in the fossil record that might indicate ecosystem disruption. You'd look for sediment layers enriched with unusual materials. But each of these proxies has problems. Chemical compounds degrade over millions of years, and distinguishing degraded synthetic compounds from natural organic materials is difficult. Isotopic ratios can be reset or altered by diagenetic processes, the chemical and physical changes that occur as sediment becomes rock. Climate changes happen naturally for many reasons. You can't assume every rapid warming event was caused by industrial activity. Extinctions also happen naturally, driven by volcanic eruptions, asteroid impacts, disease, climate shifts. The fundamental epistemological problem is that you're trying to prove a negative or detect a signal that could easily be overwhelmed by noise. If an industrial civilization existed 100 million years ago and lasted for 10,000 years, that's a 10,000-year anomaly buried in billions of years of geological history. The signal-to-noise ratio is terrible. Most of Earth's history is dominated by natural processes, so your default assumption has to be that anything you observe is natural, unless you have compelling evidence otherwise. This is the reverse of archaeology, where you're looking at recent time periods and human artifacts are common and obvious. Finding a stone tool or a pottery shard in a dig site is clear evidence of human activity, because humans are the only species that make such objects. But finding a chemical anomaly in a sediment layer from 100 million years ago? You can't just assume it's artificial. You need to rule out all natural explanations first, and that's extraordinarily difficult when dealing with processes you didn't witness and can't reproduce experimentally. Frank and Schmidt emphasize this point repeatedly in their paper. They're not saying we should believe industrial civilizations existed. They're saying we should recognize the limits of our ability to detect them if they did exist. They're arguing for epistemic humility, for acknowledging what we don't know and can't know with certainty. This has implications beyond the Silurian hypothesis. It affects how we think about the search for life on other planets, how we interpret unusual geological features, how we assess the completeness of the fossil record. It's a reminder that absence of evidence is not always evidence of absence, especially when the evidence would be hard to preserve and we haven't looked everywhere we might look. Sedimentary rocks are archives, but they're selective archives with specific preservation biases. Understanding these biases is crucial for evaluating the Silurian hypothesis and for appreciating the limits of geological knowledge. First, there's the depositional environment bias. Not all environments preserve sediments equally well. Marine environments, especially shallow continental shelves and deep ocean basins, are excellent for sediment accumulation. Rivers carry eroded material from land and deposit it on the seafloor. Organisms die and their remains settle. Sediment accumulates layer by layer, eventually compacting and cementing into rock. This is why marine fossils are abundant in the geological record and why we know so much about ancient oceans. Terrestrial environments are much more variable. Some settings, like lakes and river floodplains, preserve sediments well. Others, like mountains and deserts, don't. Mountains are sites of erosion, not deposition. Material gets stripped away by weathering and gravity, not accumulated. Deserts might preserve some sediments in dune fields, but wind also erodes, creating more ambiguous records. This means the terrestrial fossil record is patchy, biased toward lowland environments near water bodies. If a previous industrial civilization existed primarily in coastal areas, as human civilization tends to, much of their direct impact might be preserved in marine sediments. But these sediments accumulate slowly, mixing and bioturbating, spreading the signal over time. A city that existed for 1,000 years might be compressed in marine sediment into a layer only millimeters thick, and that layer would be diluted by mixing with normal marine sediment above and below. Finding it would require knowing exactly where to look and having incredible spatial resolution in your sampling. Second, there's the temporal resolution bias. Sediment accumulation rates vary enormously. In some deep ocean environments, sediment might accumulate at a rate of 1 centimeter per 1,000 years. In river deltas or floodplains, rates might be 100 times faster. This means that temporal resolution, your ability to distinguish events separated by short time periods, depends entirely on where and what kind of sediment you're examining. In slowly accumulating sediment, a 1000-year industrial civilization would be represented by perhaps 1 centimeter of sediment. Within that centimeter, everything that happened during those 1,000 years is mixed together. You can't distinguish year 100 from year 900. You can't see the rise and fall of the civilization, just an average of the whole period. And if the civilization's footprint varied over time, if they started small, grew large, then collapsed, all of that temporal structure would be lost in the mixing. bioturbation makes this worse. Bioturbation is the mixing of sediment by organisms, worms burrowing through mud, clams excavating burrows, crustaceans churning through sediment. This biological mixing disrupts original layering, moving particles up and down, smearing out sharp boundaries. In marine sediments, bioturbation can mix the top 10 centimeters or more, representing thousands or tens of thousands of years of accumulation. Any short-duration signal gets spread out and diluted. Third, there's the preservation bias related to rock type. Different types of sedimentary rock preserve different types of information. Shales and mudstones, formed from fine-grained sediments, can preserve exquisite detail, including impressions of soft-bodied organisms. Sandstones, formed from coarser sand grains, rarely preserve fine details but are good at preserving hard-shelled fossils. Limestones, formed largely from biological activity in warm shallow seas, are dominated by marine fossils. Evaporites, formed by evaporation of saline lakes or restricted seas, preserve almost no fossils but can tell you about arid climates. Chemical signatures are also differentially preserved depending on rock type. Organic carbon, which might carry isotopic evidence of fossil fuel burning, is best preserved in shales deposited in anoxic environments. In well-oxygenated sediments or in rocks that have been exposed to oxygen-rich groundwater, organic carbon gets oxidized and disappears. Certain isotopic systems are robust to diagenetic alteration, others get reset. Knowing which rocks to analyze and which measurements to trust requires detailed knowledge of preservation processes. Fourth, there's the sampling bias. We don't have access to sediments from everywhere and every time period. Much of Earth's surface is covered by younger sediments, hiding older rocks beneath. Oceanic crust older than about 200 million years has been subducted and destroyed, taking with it any record of ancient oceans from before that time. Mountain building exposes old rocks but also deforms and metamorphoses them, potentially destroying original features. The rocks we can study represent a tiny, non-random sample of Earth's history. We study rocks that happen to be exposed at the surface in places humans can access. We preferentially study rocks near universities and major cities because that's where geologists work. We study economically important rocks, like coal seams and oil reservoirs, more intensively than economically useless ones. All of these biases mean we're not getting a representative sample of Earth's past. We're getting a skewed partial view. If a previous industrial civilization's traces are preserved primarily in rock types we rarely study, or in locations we haven't sampled, or in time periods poorly represented in accessible rocks, we might never find evidence of them even if it exists. It's not that the evidence isn't there, it's that we're not looking in the right place. Finally, there's what might be called the interpretive bias. When geologists find something unusual in rocks, they typically try to explain it using known natural processes first. This is good scientific practice, Occam's razor applied to geology. Don't invoke extraordinary explanations when ordinary ones will suffice. But it also means that genuinely anomalous features might get explained away using natural processes simply because that's the default assumption. Imagine finding a layer in sediment with elevated concentrations of certain metals and unusual isotopic ratios. The natural interpretation would be to look for a volcanic source, or unusual weathering conditions, or contamination from intrusive rocks. Only if you systematically ruled out all natural explanations would you tentatively suggest something artificial. And ruling out all natural explanations is nearly impossible because we don't know all the weird things nature can do. This isn't to say geologists are close-minded, or that they'd refuse to accept evidence of previous civilizations. It's simply to point out that the burden of proof for extraordinary claims is high, as it should be, and that interpreting ambiguous geological data is genuinely difficult. When faced with uncertainty, scientists default to the most parsimonious explanation, which usually means natural processes. One of the most intriguing aspects of the Silurian hypothesis is what Frank and Schmidt call the paradox of detectability. Simply put, the more advanced and sustainable a civilization becomes, the less detectable it becomes over geological time. Consider two hypothetical civilizations, both existing on Earth millions of years ago, both lasting for 10,000 years before going extinct. Civilization A is what we might call a dirty civilization. They discover fossil fuels early and burn them prodigiously with little regard for environmental consequences. They build massive structures from steel and concrete. They produce enormous quantities of plastic and synthetic chemicals. They generate nuclear waste through weapons testing and power production. They strip mine huge areas for resources. They cause massive deforestation. Their industrial processes release mercury, lead, and other heavy metals into the environment. They drive numerous species to extinction through overhunting and habitat destruction. Civilization B is what we might call a clean civilization. They develop renewable energy sources like solar and wind power. They build primarily with sustainable materials like wood and stone. They practice careful resource management to avoid depletion. They don't discover nuclear technology, or if they do, they use it sparingly and carefully contain all waste. They manage their population to avoid overshoot. They maintain relatively light ecological footprints. They coexist with, rather than dominate, the biosphere. Now the question, which civilization would be more detectable 50 million years after they vanished? The answer is clearly Civilization A, the dirty one. Their massive fossil fuel burning would leave distinct carbon isotope signatures. Their plastic production would create a layer of persistent microplastic particles. Their nuclear activities would leave unusual isotope ratios in sediments. Their strip mining would create odd geological features. Their heavy metal pollution would show up as chemical anomalies. Their extinction of megafauna would be visible in the fossil record. They'd leave scars that persist through deep time. Civilization B, the clean one, would leave almost no trace. Their renewable energy infrastructure would crumble and vanish without creating unusual chemistry. Their sustainable materials would biodegrade or weather away naturally. Their careful resource management means no large-scale landscape alteration. Their light ecological footprint means minimal impact on other species. After 50 million years, detecting them would be extraordinarily difficult, perhaps impossible. This creates a disturbing paradox. If the goal of advanced civilization is sustainability, if wisdom means learning to exist in balance with the biosphere, then wisdom makes you invisible to future observers. Foolishness, the rapid exploitation and degradation of environment, that's what shows up clearly in rocks. Put another way, the civilizations we could detect are the ones that failed. The ones that succeeded, that achieved long-term sustainability, would be nearly invisible. This has profound implications. For one thing, it means that estimates of how common intelligent civilizations are in the universe might be seriously wrong. We're looking for signatures of industrial activity, chemical pollution, atmospheric changes, things that indicate civilization is present. But if civilizations typically exist in a sustainable mode that doesn't create these signatures, we'd miss most of them. We'd only detect the failures, the civilizations in crisis or collapse, which might represent a small fraction of all civilizations that exist. For another, it raises questions about what we should be doing now. Do we want to be detectable to far future observers? Or would invisibility be a sign of success? There's something melancholy about the idea that our greatest achievements might be invisible, that future scientists would have no way to know we existed. But there's also something appealing about the idea that we could leave the planet in such good condition that future species would never suspect we were here, that Earth could recover so completely that our passing would be like a brief illness in the patient's distant memory, barely worth noting. The paradox also affects how we interpret the absence of evidence for previous civilizations. The fact that we haven't found clear signs of industrial civilizations in the geological record might mean they never existed, or it might mean they existed but were sustainable enough to be invisible. We can't distinguish between these possibilities without additional information. This is related to broader philosophical questions about the nature of progress and development. Is industrialization with its heavy environmental footprint an inevitable stage that all technological civilizations must pass through? Or is it possible to develop technology without the massive fossil fuel burning and waste production that characterizes human civilization? If alternative paths are possible, paths that are lighter on the environment, then the absence of obvious industrial signatures in Earth's past tells us very little. There's another angle to the Silurian hypothesis that deserves consideration: the statistical problem of detecting rare events in limited data. Suppose that industrial civilizations are possible on Earth, and that they arise randomly at some very low rate over geological time. Let's say, for the sake of argument, that the probability of an industrial civilization arising and lasting long enough to be detectable is 1 per 100 million years. This is entirely speculative, just a number to work with. Earth has had complex multicellular life for roughly 600 million years since the Cambrian explosion. If civilizations arise at a rate of 1 per 100 million years, then we'd expect about 6 industrial civilizations to have existed during that time. But here's the problem. We can't look at all 600 million years with equal resolution. The older the rocks, the less access we have to them, the more fragmentary the record. Let's say we have good access to sediments from the last 10 million years, partial access to sediments from 10 to 100 million years ago, and very fragmentary access to anything older. If industrial civilizations are randomly distributed through time, most of them would have existed in time periods we can't study well. We might have evidence for 0 civilizations, even though 6 existed, simply because we can't access the right rocks. This is a sampling problem. You're trying to detect rare events, but your ability to look is limited. It's like trying to estimate how common shooting stars are by looking at the sky for only 1 minute per year. Even if shooting stars are common, you might see 0 during your limited observation time, leading you to incorrectly conclude they're very rare or non-existent. The situation gets worse when you consider spatial sampling. We've only drilled cores and examined rocks from a tiny fraction of Earth's surface. The ocean floor, which covers 70% of the planet, is largely unexplored in detail. We have some deep ocean drilling cores, but they're sparse, covering perhaps 1/10,000th of the ocean floor in scattered locations. If evidence of previous civilization exists in ocean sediments, it could easily be in locations we haven't sampled. Continents are better explored, but even there we're limited. Sedimentary rocks older than the Quaternary are exposed at the surface in only certain regions. Much of the older rock record is buried under younger sediments or has been eroded away. The rocks we can access represent perhaps a few % of all the sedimentary rocks that have ever existed on Earth's surface. So we're looking at a few % of the surface with good temporal resolution for recent times, but fragmentary resolution for deeper time. Trying to detect events that might occur at very low rates and leave subtle, ambiguous signals. The statistical power of this search is low. Even if previous civilizations existed, the chance of detecting them given our limited sampling might be quite small. This doesn't mean previous civilizations definitely existed. It means we can't confidently rule them out based on absence of evidence, especially if they were rare and our sampling is limited. The distinction is important. Saying we haven't found evidence, therefore they didn't exist, is only valid if your search would have found evidence had it existed. But if your search is incomplete and biased, then lack of evidence is inconclusive. Statisticians would say this is a problem of insufficient statistical power. You need adequate sample size and appropriate sampling strategy to detect rare events. We don't have that for detecting ancient industrial civilizations. Our sample size is too small, our sampling is biased toward recent and accessible locations, and our detection methods are imperfect. The only way to improve this situation is to sample more locations, develop better detection techniques, and specifically look in places most likely to preserve evidence. This means deep ocean drilling in multiple locations, examining sediment cores with fine-scale resolution, developing analytical techniques sensitive to industrial signatures, and doing systematic surveys rather than opportunistic sampling. Some of this is happening. Ocean drilling programs have been running for decades, slowly building up a library of deep ocean cores. Analytical geochemistry is advancing, allowing detection of trace elements and isotopic ratios at unprecedented precision. But it's slow, expensive work, and it's not being done with the specific goal of finding previous civilizations because most scientists don't expect to find any. The search is not systematic because the target is considered implausible. But the Silurian Hypothesis suggests maybe the search should be more systematic, not because we expect to find evidence of previous civilizations, but because looking carefully would test our assumptions about geological preservation, give us better understanding of deep time chemistry, and perhaps reveal interesting natural phenomena we didn't expect. Even null results would be scientifically valuable, constraining the parameter space for how detectable industrial activity is over geological time. If you're ready to keep exploring the biggest questions in science, hit that like button and subscribe. We dig deep into topics that challenge everything we think we know about reality, from the edges of physics to the nature of consciousness to our place in cosmic history. The universe is stranger than we imagine, and understanding it requires questioning our assumptions and following evidence wherever it leads, even to uncomfortable places.